Everyone, we got a new setup, so hopefully trying to green screen really well right now. But let's see if we got anyone in the chat, and let's see if everyone can hear me pretty well. So is anyone here? Can anyone hear and see me? How are we doing in the chat? And can anyone hear and see me? So hopefully we're getting a new microphone stand and trying to green screen as well as I can. Small room and lots of lights. So if anyone can hear and see me, maybe it's just a test stream today. We'll see if anyone is here and has questions. I sent out the link to students, so we will give that a check. But I have to lean in this way to make sure I'm on the microphone. I want to hear how everyone's hearing the volume. So we can go over here. Some stuff to show off. I know 474 is working really hard on their assignment due Tuesday night. So let's go show something off right here. We have a very, very helpful thing, a R file. Let's bring back up the chat, see if anyone's here. We have a very, very helpful R file that everyone can utilize. So the R file I would definitely suggest taking a look at is going to be, where is that help with caret file? Did it go away? It should be on here. So basic modeling, here it is down here. So we have right here using caret to train predictive analytics. So using models to tune for caret. This is a huge helpful file right here. This file is key in making sure you know what to do. I just noticed I'm looking like off to the side all the time. Now I wish my monitor was easier to look at. Now it's off to the side. So let's take a look right here. You can do the PDF or you can do the R file. I like the R file a lot more, and I'll explain why. Because you just get the R code, and that's what you're going to be utilizing. So you'll be utilizing the R code, and we can see it right here right now. So with the R code, and hopefully I'm close enough to the microphone, I'm gonna have it like in front of me later on, like when I don't know, hopefully it won't block the screen. But we'll take a look down here, and what do we have? We have a lot of stuff. So everything you can notice right here is a lot of stuff. But what I like to do is I like to Control F through this. You think about what you'll be doing things like subsetting, so you can do train rows through this, which is what we often do. And if you look right here, there's doing if statement on train rows, but here we go right here, storing train rows, a sample size of this. So there we go, just making a certain amount of train rows, and then you can see that's still the if stuff right here. Here we go, find a new part right here. There we go, train rows sampling. So there's just taking a sample right there. You can usually find what you're looking for pretty quickly if you just go through, and here we go. This is the kind of code I'm looking for. Now I've written this out in class before, but this is making a subset right here. And you'll notice we're just pulling up, let's take a look at it. We're setting our seed to control the randomness. Before that on line 320, we're bringing up reg class to start up that library. We have data ex7 bike right here, which is a data set inside of reg class, and both of these are appended onto each other, so we're running them both together. Then we have set seed right here, and that's just controlling the randomness. Then we have the train rows, which we are creating by taking a sample of the numbers 1 through how many rows there are in ex bike, and then we're only taking 60% of those. So on the next line, we're going to store our train subset, and this is what you're doing in your assignments, is you're going to create a train subset by going inside of ex7 bike and only taking the train rows. Now the holdout, I think I made a mistake when we were doing this because I didn't change this to the minus. You'll notice when you create these things, you should see ex7 bike loads is 410 observations. So you do a little quick mental math in your head and you think, okay, what is 60% of 410? Well, that'd be 6 times 4, which is 640 times that. So I think it should be, my brain is so slow this morning. I think it should be, so 645, 686. Is it going to be 686? Let's find out the hard way. 686. What am I saying? But it should be 60% right here. And you're noticing that we're just creating a subset of only train rows that we're going to make our model with, and the holdout will test the model. So it makes sense that this is 40%, this is 60%. And my mind just cannot do math this morning. Yeah, 4 times 4 is 16, and 4 times 1 is 4, so there you go. 4 times 6 is 24, and 1 times 6 is 6. There it is right there. There's 60%, there's 40% of the rows. And if anyone's in the chat, feel free to say hey, and we can start doing some problems that you're stuck on. So we got right here the aggregate function, which is going to show us all the medians of demand by day. Aggregate's such a cool function because what it'll show you is it will create a table right here, and you can change this right here to something like mean, and you can get the mean of it, and there's the mean. You can change it to whatever you want. You change standard deviation, and we have a object not found because we're using something different right there. So we'll go back to the original aggregate, and you can see right here, this is just going to show us the standard deviations now. So aggregate's a really fast, really easy function. It's just y tilde x comma data equals, and then we do function equals something. So we have to do y tilde x comma data equals, and then comma function equals something. You can add more things in here to the x. What are other things in this data frame that are categorical? We've got day. We've also got, that's it for category. Oh wait, working day. So we can go right here and go working day. It's also kind of inside that variable, but still, now when we make our table, see there's not applicable, and we're probably going to get that. Oh, yep. Well, are they all working days? Saturday, oh yeah, because there it is. That's weird. So Saturday was a working day on some of those days. Really interesting, didn't know that about this data set, but now you kind of get a much more bigger way of aggregating. So what else do we have? All these things create dummy variables, all that good stuff. Let's go down here to the fit control, which is a huge thing. And I really love this part of it because in the fit control, you can see exactly how we're making them with notes on them. So we've got here no estimated generalization error. So that means we're going to get no validation right here. So method equals none. We have 5 k-fold cross-validation. So you can see right here, there's just the general command. And then we have here repeated k-fold. So if you like doing k-fold cross-validation, why not repeat the method multiple times? So you'll do 5 k-fold cross-validation, and you'll repeat it 10 times. So that's all it is right there as we click into it by accident. So this is just the fit control to kind of control what's going on. And by control, I mean to choose the model you're going to make. So this will help us choose our model. We have right here the train control. Now this changes. I want to point something out, that the biggest thing right here is in this section, we're doing it for categorical. In the top one, we do it for quantitative, and the bottom one, we do it for categorical. And you'll notice things like here, class probs equals true. Now with class probs equals true, you can see it over here on this one all the way up the side of the screen, class probs equals true is going to do accuracy. I was like for people to remember when you want to do AUC, ROC, which pretty much mean the same thing. AUC is area under the ROC curve. So it's actually, when you think about AUC, it's actually this. It's area under the ROC curve. It's actually the numerical calculation. ROC is the graphic. What do I mean by all that? Let's go over to our Word document. Let's take a quick look at it. Should have our pen right here. So, and if anyone's in chat, say hey. So we have right here the ROC curve, and then we get the area underneath it when we make this graphic right here. The graphic will, why not space pen? So the graphic will look something like this right here. And this area, which would maybe be about 60-65% right here, tells us kind of the accuracy in ordering our true positives over the false positives. So we want to look at our true positive rates over our false positives, and we want to get all the true positives, go through all the true positives before we go through any false positives. So if we do that, it'll look something like this. At that point, we will have captured immediately. Hey, what's up, Julio? It's so good to see you. Just got to unpack. Yeah, that's awesome. I have created a studio in my house now, or my house, my apartment. I've created a studio in my apartment, so I'm currently broadcasting from there, and hopefully everything sounds good and looks good. I've got new stuff coming in. I've got another light, so hopefully the green screen gets even better lit. You can see a little bit of fuzziness behind me. I've been working on it. It seems like every time I adjust it, it changes on me. But anyways, good to see you. Looks awesome. Thank you so much. It looks more like we traditionally have it. And watch this. Julio, you're the first to see this. I can raise my hands up all the way. So I can raise my hands to the ceiling almost. I mean, the ceiling's way higher, but I've got more room to the side. You can see the bright light right there, but I've got a lot of room around me right now at the green screen. So awesome. And yeah, we'll figure out a time for the interview and everything. So good to see you. I know way more room, way more. I was trying to put like a way more room for activities thing on here. So I need to shave. I haven't shaved and my face is like, what is going on? So anyways, good stuff. I'll be here. I don't know, maybe a 474 will come by, a 201 will come by and want to do some problems, but hopefully it sounds good and looks good. So yes, I just can't, I think it's because I'm so close to the green screen, it's having issues. if you can see the green screen through the back of my chair. When I move the chair, you can see it over there on the corner. Oops, I gotta go this way. You can see the green screen through the chair. So, all this good stuff right here. Let's take a look. So the biggest thing with the fit control is what it does is it sets up how you're doing your validation. So when you figure out how you're doing your validation, you will choose between either quantitative or categorical. So you've got your quantitatives up here, and there's more ways of doing it. These are not the only ways. You can use boot. There's so many ways. Like, I haven't truthfully even looked at all the ways, but choose the way that works best for you, and make sure it is proper for what you're doing. If you're doing quantitative, you don't want to do the following because this fits to accuracy, and accuracy is a measure for categorical variables. If you're doing quantitative, you don't want to do this because this is a measure of ROC, AUC. And once again, these are the same thing. They are just interchangeable words almost, because AUC stands for the literal, oops, PowerPoint's opening up, layout. AUC literally stands for the area, that's the AUC, and then the curve itself is the ROC, the receiver operator curve, and the AUC is the area underneath the receiver operator curve. So same word, not same word, but same thing, different words. And so once again, make sure you're doing the right stuff right there. Now, one big important function that we use throughout all this is the train function. So there's a bunch of train control, and I guess I should type in something a little more specific. There's method like GLM, there's the GLM method, there's method like k nearest neighbors, there's method like support vector machine. So here's a polynomial support vector machine. I believe this is our next chapter. And if you notice right here, all we're doing is saying method support vector machine poly. And that is the kernel it's going to try to fit to this to figure out an additional dimension to put a hyperplane through it and create separation between the points. There's so many things to talk about this. I don't want to do the full lecture right now, but it's going to look for the correct hyperplane to put through this data in an increased dimension. And so it's really not that hard to write these codes. Thank you to Hadley Wickham, who figured out that we just use our regular format of y tilde x comma data equals comma method. If you'll notice right here, and all of these follow this whenever we look at them, we will just have train control equals fit control, and then we need this is the big thing people forget, is we have a tuning grid. Now the tuning grid is going to be what we're going to search through. So let's take a look at what's in this tuning grid pretty easily with this. Oh, I'm still inside of, I don't know when that happened. I was inside of stuff. We don't want to do that. So, oh, it's right there because it's all hashtagged. That's why. So let's start doing this. There we go. And now let's go get the parameter grid. There we go. Okay, so here we go. And we can see here that we've got the degree, the scale, and the cost right here. So we'll talk more about this in a later class, probably this week, next week. But these are the values it will try when it's trying to fit this model right here. It'll fit these all on the training data. It'll see how it does in the validation portion. And then we'll select the best model when we do this right here. We'll select the best one, and we should be able to, as long as the data is loaded up. So this is using there it is, data train, but it was made from, where was meat weight originally made? We could look at this. We haven't done it yet, but it'll show you how it's done. This is done via the meat weight is ex4 abalone. So abalone. So we can go to where, there it is. Here's the data ex4 abalone, and here's creating some train rows from it. So there we go. Set seed not found. Oh, because we put it up here. There, just didn't run one line of code, and that's how everything goes. When you get a chance, how do I get the answers to test 2? It says empty. Oh no, let me take a look at that. Hopefully it's working, Julio. It should, oh, you might be looking at test 2. Look at the respondus thing. Go to quizzes. And I'll check this out. I probably can't do it on stream because I'd be like going into like grades and stuff. But it should be it should be like under your quizzes. So test 2 is like where I copied the grade to, but then it should be under like quizzes, and maybe you can view the quiz. So check that out, see if it works. Get back to me if it doesn't, but give that a try, and we'll see if that does it. I'm unsure since give that a shot. Like go to quizzes and see if you can click on that quiz. And so there we go. Great question, Julio. You're welcome. Yeah, you're the only person here, so you get all the questions. I'm just kind of making a video to hopefully help out 474 because they're working away on all this right now and trying to solve how to use all the code. And it's a lot of code. Like knowing what it does is the important thing. So all I did right here by running all this code right here was I set a seed number so I can use set seed later on. See, this could just be, usually a lot of times we just write like that. So like you don't even need this seed here then. So seed's already saved, but I could have ran it like this right now. And so now we're making the training of the holdout. And I'm gonna stop, well, we're gonna need this right here. So we're gonna do a quantitative, and that makes sense because we're predicting meat weight. Meat weight is a quantitative amount, and you usually wanna check this. So could not find function, tr control, because library. And then we need caret. There we go. Cool. So we should be good now. You just have to know where your functions are at. That one, I think, let me try something. Glimpse. It won't show me glimpse right now. Glimpse is in, I thought it might, because glimpse is in dplyr, but I don't have it loaded. So now if you notice, glimpse loads. Glimpse is a really quick function that lets you glimpse a data set by glimpse. I mean, you get to take a quick look at it, and you can see the variables. So we can see that meat weight is a quantitative variable. So knowing your functions, knowing where they're at is key. If something doesn't run, you always have to look at the error and just take a look at the error we saw. It said could not find function train control. So that's going to mean I spelled it incorrectly, but once again, I'm using notes. So I would assume that it's spelled correctly in the notes. You can assume that, you're not always right. But I would then think maybe I haven't loaded that function because R loads with kind of vanilla or base R, and you don't get all of your functions to start. So I have now loaded up the function, and once again it runs. We'll just show again that runs perfectly fine. So now what I'm going to do is I'm going to go to the k-nearest neighbors. Not k-nearest neighbors. I'm going to go to support vector machine. Support vector machine right here. I believe this is one we were running before. We're going to unhashtag out these. This is a polynomial support vector machine, and if you notice what it's doing, let's look at the expand grid right here. Oh, we didn't unhashtag out that. So when we look at what this is doing, this is for later on, but why not teach it right now? What it's going to do is it's going to create a grid of numbers we're going to try. So all this line of code does is the expand grid is the tuning parameters we're going to work through. So the expand grid right here is going to create just different, think of it as knobs on a stove, as in you could turn this knob up, turn this knob down. You can just do anything with the knobs. You can just start turning them whichever way you want. And we're trying to find the best setting to bake a cake on. So there's a timer knob, there's a temperature knob, there's a moisture knob. I can't even speak. But there's all these different knobs and like just dials on the temperature and dials on how long it'll cook for and dials on the humidity and dials on the, I don't know, dials on the sprinkles. We've even got our sprinkles dials for the cake. So you can turn the sprinkles up or down on the cake. You can turn it between vanilla, chocolate, or strawberry frosting. And you're going to do that after you bake it, of course. But there's all these different things you could change. And that's what the expand grid is. It's all these different values you can try out for making your model. So we're going to put them all on a grid because it's like, imagine if I told you, we'll do a very easy problem here for those watching this, because I hope people use this to do their assignments. But if I told you I can bake a cake for a long time or a short time, that's all you can pick right now. So your long time cake is going to be it's going to be dry, it's going to be harder around the edges, and your short time cake is going to be, don't worry, no salmonella, but it's going to be a little like softer and maybe not totally cooked, but still safe to eat. But you can see the difference right there. We got a longer cooked cake and a shorter cooked cake. And then we have one of them is going to be chocolate batter and one of them is going to be vanilla batter. So if I said how many combinations are there, we could do a really quick version of this. We could go expand grid. So we got to type it in properly. And when we go to expand grid, we're going to put in one thing right here. We're going to put in flavor. And we're going to go here to chocolate, comma, vanilla. Say I spell vanilla? Close enough. People will know what that means. But I am going to change one thing. I don't like that it's in the parentheses I don't use. Both of those will work, but that's my favorite. And then we're going to put in a second variable. You can do it like this. Sometimes I like to make my code look where it's very easy to see what's going on. Like this is the first variable, this is the second variable. And then the second thing I think I said was length of time. So let's go length time. We'll do an underscore there. Good practice. So length of time, it's going to cook, and we'll go short. and we'll go long. So I just want you to think for a moment, how many combinations are there of the way you could cook this cake? And if anyone in the chat says it, I'll give you a million points. I don't know how many people are watching, if anybody right now. But we've got chocolate, short, chocolate, long, vanilla, short, vanilla, long. That's all the expand grid is doing. So when we take a look at it, there it is right there. I didn't do it in the right order. Doesn't matter because we're just going to look and see how they all do. It doesn't matter to the model which one it does first. It doesn't matter to R which one it tries first. So I guess the algorithm is chocolate, short, vanilla, short, chocolate, long, vanilla, long. It kind of permeates through the first variable. So we could think, what if we had another variable here? We go sprinkles. Now, with sprinkles, I'm going to put in 3 levels to sprinkles. I'm going to put in low, medium, and you're probably guessing it right now. We're going high, and I've been capitalizing. I'm a huge person on the consistency of how these are written. It just, I like it to have the same exact format each time. So it's probably going to go chocolate. Let me make sure I do it in the right order. Chocolate, short, low. Vanilla, short, low. Chocolate, long, low. Vanilla, long, low. Chocolate, short, medium. Vanilla, short, medium. If you can't see, I'm permutating through, and then it'll go chocolate, long, medium. Vanilla, long, medium. Chocolate, short, high. Vanilla, short, high. Chocolate, long, high. Vanilla, long, high. And let's find out. And this should be 2 times 2 is 4 times 3 is 12. There we go. And if you notice, it permeates through, like chocolate and vanilla keep flip-flopping, and then it goes through the short, after it goes through the short, it goes through the long, and then after it makes the cycle here, it switches this variable to the medium. So you don't have to know how to write it like that. The bigger thing is to know what it's doing. Like, you don't have to be like, how exactly would I write each of these? What would come next? I was just having fun because I don't know, it's a puzzle. So let's solve the puzzle. How does it work exactly? So you do need to know that this expand grid would give you 12 combinations. Why 12? We did this in class because this has 2, this has 2, and this has 3. So 2 times 2 is 4, times 3 is 12. There's 12 different combinations of how we can make that cake. So we can look at this one right here. We've got expand grid of 2. And this one right here is length 5, so that gives that away, and this is length 3. So that's 2 times 5, which is 10, times 3, this should be 30. So we look at how many combinations we have, and there are 30 combinations in this expand grid. That's a great test question right there. Like, look at the expand grid, how many combinations will you get of models? Boom, 30. If you notice, if you know how to do it, it's an easy solve. It's saying, well, it's going to make all the combinations of those, and we know it instantaneously. Now, although we haven't done support vector machine, we can make sure we know what the code does. So with support vector machine, we're going to set the seed so we get the same result. Haha, hope that happens every time. And if anyone's here, say hey, and we're just kind of working through a little forcing for talking about it right now. So we've got here, we're just storing it into this. This can be called anything. You can just call it any name you want, your name, whatever. So I thought I misspelled my name for a second. Everyone does that, including myself. And we have right here what the function is. This is the train function from reg class. If you don't believe me, go down here and type train, and you'll see it's in, reg class, it's in caret. I don't believe me either. So we've got the train function inside of caret. Once again, you can see what something's inside of by looking over here, and you can see that says caret. So this is the train function inside of caret. So we've got the y variable right here. This is the formula format, y tilde x. But we're doing a dot because we want all the variables. So when we do dot, we want every single variable inside of here. And so we've got y tilde dot, and that means every single x variable will be attempted to be used, and we'll see what we get right here. We've got data equals train. This is because we're doing a predictive modeling. If you're not using train, you're doing it wrong. Then we've got method equals support vector machine polynomial kernel. And so there's other support vector machines, but right now there's the Gaussian, there's the linear, there's the polynomial. Gaussian means the normal model or like bell-shaped curve. So we've got all these different options right here, but we will use the support vector machine polynomial just for this example. So we've got the train control equals fit control. This is where we're seeing how it works on the validation. We've got the tune grid, which is right here. There it is. And then we've got the preproc. That's going to make everything into z-scores because we are center and scaling all the data. That's going to give all the variables an equal say on the model, and we've talked about that a lot in class. So we go ahead and run it right here. Packages needed, sure. New R just helps you out. And so it looks like it's running the model now in the background. Some of these can take quite a while. The amount of algorithms we can do now, the intensity of the mathematics to solve problems just blows my mind. And that's why you go back 20 years and we really couldn't do the super advanced, partition models like extreme gradient boosting or these really cool support vector machines. We would be kind of stuck, not stuck, but we would be like, oh, I guess we got to do regular old regression, or I guess we could do elastic net, which is your GLM net. So GLM net is the lasso ridge trade-off regression where you have your alpha and your lambda, and those would be tuning parameters. So I think everything's downloading. I think it downloaded. I think it's running the model right now. It's just literally, this is not a complex problem, but it can take quite a while to do. And what I'm going to do after this is I'm going to turn it into a 320 problem. I'm going to see how we do on the 320 problem. So I'm going to turn this same problem, because I'm interested, to see how it does on the 320, and using only what you know in 320 to try to solve this problem. I think it's running it. It's just literally like I keep saying as we talk about this. And let me start writing a little 320 code while this is going on right here. So if we want to predict meat weight in 320, we might use a stepwise regression. Now we're going to do it on the train model right here. Let's see. So we're going to make a stepwise regression. And let's make sure I can get this by memory. We've got step. Is my autocomplete not going? Let's see here. Step. Oh, should be step. Maybe it doesn't work right now. Maybe while it's thinking in the background. And this is a really good computer. Well, oh, there's step. There we go. Step, step. Let's try this again right here. Step. Step should allow us to make a stepwise model, and I think my computer is just really thinking about this support vector machine. Wow, support vector machine. There we go. Step, object, yes. So a few things we need to do a stepwise model is we need a naive model. So I'm going to have to write this but not run it yet. We've got right here the stepwise model, and we need a naive. A naive model is going to be nothing in the model. So we're just literally going to take our data right here, and we're going to create a linear model, do this, but now we're going to put nothing in it. The 1 stands for nothing. So there is a stepwise model on the training data with nothing. We're going to copy this code, we're going to paste, and then we're going to make a full model. So all we have to do to make this into a full model, if you saw that F was blue because it was treating it as a false for a moment, is we're just going to put in every variable. So now we have 2 models here that will run eventually, a naive model and a full model, and these are kind of your fences. For anyone who's trying to remember 320, we're going to step through the variables in these models to see what would be the right amount of variables, and we're going to make it on the train right here. We're not doing a validation right now. We're just going to see kind of if we didn't use predictive analytics and we kind of found the best model, how would it actually do? And hopefully everything's going on. I think it's running the code because it asked me if I wanted to run it. It's just that some of these can take quite a while. So we'll cross our fingers. I might hit stop eventually. Let's see what it did. So the first thing with a stepwise model is where are you starting? So, and we'll make that go away because that's not helpful right now. So the stepwise model is going to start with the naive. And then let's see here. We need to go to scope equals list. And then we go right here, lower equals naive. Should be in quotes because it's going to grab this right here, and then upper equals full, and then we go one more over, and we go direction. So I'm going to get my autocomplete. Direction equals both, and when the support vector machine runs, eventually I might just take a look at the results right here. I'm wondering. I know support vector machine can take a while, so it is crazy the amount of algorithms that are happening in the background right now. And I'm thinking this is such a good computer, I wouldn't expect it. Oh, right then. And this is a really good computer. So, wow. Wow, that took a while. That took like 5 minutes. Support vector machine, what are you doing? There we go. There's the results right there. And you notice, I think, once again, what's crazy is they've updated the randomness inside of R. So we are seeing a little bit different of results right here. So sorry that the notes, like we have tons of notes and tons of things to update. If you notice, this is like 1,000 lines of code with output. But because the randomness procedures have updated, and sometimes like caret will update, so they might update even how it works. But so that's why sometimes when we hard code in an answer, it's a bad idea. But we do see, let's take a look, the degree was 1, the scale right here is 10 this time, and the cost is 10. So it actually shows a different model, just barely off on the scale, a little bit different, but very similar support vector machine. So what I should get right here, error naive not found, of course, because I didn't make these yet. There we go. Okay, so now I've stored a model into here, and let's just see how this did on the data it was created from, because this is the best results here. And so what do we get? Pretty similar. So we'll see if we overfit though, because we're going to see how it works on the holdout. We should be able to do post resample. We've got an RMSE right here, which is the root mean squared error. And actually, and this does control for how many variables you put in the model. We are seeing that the RMSE of this model here that we made, well, that's not the results. Let me look at its actual results. The RMSE of this model is 0.3053, and the RMSE of this one is 0.3068. Wow, so they're all very similar, and they probably all, where's the RMSE standard deviation? They're all very close to each other. If you notice how the RMSE standard deviation tells us our uncertainty in it, so all these models I created are very, 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 very similar. So, and I would increase the tuning grid on this support vector machine to see if it worked better. Let's look at how it did on the holdout. Hey, what's up, Connor? I've been going through talking about these notes right here, having some fun talking about, whoa, now that's really good. This right here is how it works on the holdout. And so we've got our holdout, and I wonder, let me try this. Yes, it does work nice and easy. So, whoa, that's so close. And this was all done, ask questions if you got them, Connor. I'm kind of shocked this worked out as well as it did. I made a stepwise model, and I made a stepwise model really quickly, and I made a support vector machine model, and both of them work nearly identical. It's probably because there's just a really good combination of variables. The support vector machine, I hate to say such things, but as long as it ran, it was kind of a waste of time. It was like someone pulling out a $10,000 screwdriver and being like, let's screw this into the wall with this $10,000 screwdriver, and you're like, the $10 one works just as well, and they're like, well, it works a tiny bit better. And what do I mean by a tiny bit? It's got a tiny bit higher R squared and a tiny bit lower root mean square error, and also the mean absolute error is a little bit lower also on the really, really great, like super powerful one. So it did do a little bit better. If you notice, Connor, we're on a green screen today. We got the green screen up, so hopefully you can hear me nice and well. But how are you doing, Connor? I kind of just went through how to use these notes, and also did some good old classic 320 in the middle of here, which I was surprised it worked that well. You're doing well, awesome. I also did 320 with predictive analytics, but I didn't use a validation portion. I just literally made a stepwise model and then saw how the stepwise did. But I didn't even notice the green screen. Oh, really? It's just, well, and then I need to fix it more. You can kind of, I'm glad you didn't notice. I'm so used to it. That's awesome. Watch this though, Connor. I can raise my hands up all the way, and I can put my hands over here to the side. Now there's a light over here, as you can tell. That's why it's all bright over there. So, but that is, we've got a lot more room right here. So I'm not just in a tiny little, my face, but it's hopefully a little bit better. And yeah, and I've got, hopefully the audio quality is good and everything. You dig the Mega Man t-shirt? Yeah, you can actually see my t-shirts now. So I was like, I'm gonna wear Mega Man today. I haven't worn it forever, but yeah, I was like, I don't know. That's awesome. Mega Man's like, do I have any of my Mega Man games are over there? But Mega Man is like one of my favorites. I've got a bunch of like nerd stuff to put in the background, but I should like find like some people do that. They put their stuff out, and that's one way of like putting out a cool room, or you can green screen yourself. So I'll figure out what's going on. Like once we build the studio in Texas, once we build the room in Texas with all the stuff. I say studio, we're not building like a massive studio. But what questions do you have, Connor? How are you doing? We'll see. I've done like 30 minutes of, I hope this video helps out a lot. And sorry, there's small issues with sanity checks and stuff. On 1B, the naive model would predict for purchase level no, correct? Yeah, I think so. Let me, do I have that one up? Let me go over to Let me go over and look at that. So we've got all this here. I'm going to bring it back over to here. And yeah, so right now I can't see the screen at the moment. Let me go get, this is, it should, if we're doing purchase, do most people not purchase? That is what it will predict. So we're still on basic classifications. I feel like we should be beyond this assignment. Here we go. We're doing basic classifications, right, Connor? Is that correct? I've been looking over so many things. Yeah, I'm 99% certain. This is the one. I know that training will hold out really well. So, because of the sanity checks. So, the easiest way to know what we're predicting right here, let me bring back up the chat so I can see it. So, yeah, we're going to predict the majority level. That's what the naive would predict. So if you go in right here, we just can load in all the packages. Do I have all of these on this computer? It looks like yes. Good. This computer I don't do a ton of our work on, so I never know if it has every package I need. And now we go to data and we go to summary of it. This works for figuring out. We go to purchase, and the answer is purchase no. It's purchase no because that's the majority level, and that's what the naive does. The naive will do the majority level. I was doing this one right here with a few people. So with this one especially, the reason we can't, if you do like log 10 of like -5, I think that'll, yep, warning message produced. It doesn't like it. So I think, and this should give, will this give negative infinity? Yep, negative infinity. So you can't really do that. What we want to do is we want to put everything that the lowest value is log 10 of 1, because that'll give 0. So our goal is to take any sort of thing right here in accounting, and we would go to, let's just go to accounting, and let's go to, I think checking balance is one of them. Let's go ahead and look at a summary of it. And when we look at the summary, keep asking, it took me 20 minutes to figure out why apply was returning the wrong values on A. So yeah, apply accounting. So you're doing rows, columns. So was the wrong value on A? Was that seems similar. Let me see what's going on right there with that. So there's that, and let me look at that code. Apply, and so you're taking the data frame account, and then you're doing not rows but columns, and you're doing the min right here. And so we see right here, because some of them are, is it getting mad because of the categorical nature of some of them? So that's interesting right there. And I noticed saving balance accounting, because we're not getting the minimum of checking balance right here. It's treating it as a, I think it's treating it as a word. I think that's the problem. And so -1, I don't think it's a coincidence that the ones are here, because I think it's treating it as a word. Yes, string, exactly. And so, lowest hex value, that might be it. I think you're right. You're right. Look at the zeros. Yeah, I don't think that's coincidence that we see 0 zeros there. And yeah, like the lowest hex value. Yeah, I think you're right. That's weird. So what you'd want to do is this is 2, 3, 4, 5, 7, 8. So let's go here and go, will this work? There we go. And so wait, I put it on the wrong thing. I put it on the wrong set of code. Okay, so that's still not doing it. Let's just go down a lot smaller on this. And it's still doing it that way. And so what we probably want to do, here, let's do this. Let's go quant, and the quant, I think if we do this, and we only make a data frame of our quantitative variables, and what we'll do is we'll cheat with glimpse. So our glimpse is going to show us what is quantitative here. We could probably do it with a, so wait, 2, 3, 4, 5, 7. 2, 3, 4, 5, 7. So we go here, and then we go, yep, that's right. 2, 3, 4, 5, 7. Okay. And then we take quant. There we go. So is that correct now? Checking balance has -774.83. And then the other ones have those. So I think this will do it right here, yeah. Because since there was, as you were pointing out, characters in there, it can't take the min of a character. So it looks like it is trying to return the lowest hex format, hexadecimal. Yeah, so complicated to be like, okay, what is going on? Why are we getting these numbers? I think the clue is right here that we see these zeros, so it's some sort of hex format. And then all we do is we take the quantitative values, and you could write a bigger thing, like you could turn this all into a function and do all this cool stuff with this, but we're just trying to see for the moment, you know, probably the best way is to see if it is numeric, which, you know what, okay, let's try this. Let's practice our skills. So we should be able to take apply, and let's go to apply and do the following. Let's do account, and then we want to do it on the rows, and we should be able to do is numeric. We'll get all false. Is dot integer. Is infinite. What is that? So that's not returning trues on that. I don't know why it wouldn't. I'm trying to think, because I would think we could check them. What do you think about that, Connor? Because I would think we could check them to see if they're numeric, and we could store this then as a vector. So the first column was of double type. Would the apply function treat the remainder of the data from as numeric? Yeah, let me take a look at that again. Let's pull up the glimpse. And there should be a way to check. So double decimal precision. Hey, what's up, Christian? We're just working away here, talking about the assignment sum. Any questions you have, feel free to ask, but good to see you. You think it only evaluates the first column? Let's see right here. So the first one was factor. So we should be able to do is.factor. No, you see, it's not even doing that. Well, that'll turn it into a factor. That's not what we want. And rows and columns cover doing that. Is.character. Okay, it might be just looking at the... It says they're all character, but that's not evaluating the data. You're welcome. You're so welcome. Sorry, I know it's a lot. I'm always glad to help you guys out. Keep emailing me. I really appreciate it. I answer a lot of emails now, and I really, really appreciate it. Like, I want everyone to feel like there is help, and I thank you so much for all the hard work. And if you ever feel like you're not graded fairly, like, I know the sanity checks are a little bit of insanity checks sometimes. Just tell me, and we will do it. And you can find me online at these times, and I'm just here to talk and to help people out. So, and to figure out why this code's not doing what I want it to do. Like, that's what I'm thinking about right now. Because I'm like, why will this code not do this? I mean, I could do it with like a subset. That would be not a fun way of doing it. But what do you think, Connor? It says they're all character. I think it's just looking at the name, like it's looking at the column name, and it's treating the column name as a character. But I don't want it to do it to the column name. I want it to do it with the columns themselves. So, I mean, I'm thinking in my head, that's the only reason I think it would treat, because it's saying it's character. I mean, it has to be something. The object has to exist somewhere. So it's not evaluating the data inside there. It's just evaluating the column name. Try doing is numeric on quant. So on quant, okay. So you're saying just take this right here and go in quant. Oh, what is going on? Hey, Rachel, go over the questions about the maze times for the conference roles. Yeah, we'll do that. We'll do that next here. Connor, come up with some more questions, but Connor, figure out this code. I'll give you 1,000,000 points. I wish I could do it on account. So we'll do the StatTool1 rat time maze thing right here, and maybe I'll do it in 320. You're welcome, Rachel. So good to see you. Let's hop over here. I'm going to bring it up right here so I can't see the chat for half a second. It'll be hard to see. I got a third screen, but it'd be really hard to see because I've got a light. I'm going to figure out how to make these lights perfect in here. So I'm pulling up the confidence interval rat time maze one. I'm going to solve it a few ways right here. And so we will talk about this. And so I'm pulling this up right here. We've got the new green screen. And I wish I had a standing desk. That'd be a lot of fun. So then we go over here. I'm almost got it up. Let me make fonts bigger so I can see. Okay. And so we go to chapter 14, confidence intervals for the mean. This is the quiz. Let's go to the preview on it. And let's go into here. Okay, so Rachel, we should be able to see this now. And here we are. Okay, we are back. So, hey, Brian, Yeah, we can do that. I think we'll be doing that tomorrow, Christian. I think we'll be doing that tomorrow. You'll be back soon, Connor. Awesome. Whoops. Maybe I got lucky and got it, the rat maze one, but I didn't click on all the questions. And the answer is nope. I have to click on replace questions. Oh my gosh, I got it. So we got it. You're welcome, Christian. So I think we'll be doing that tomorrow to focus in on and make sure we understand what's going on. So I think that'll really, really help out to do the next lab right there. Finding 95% confidence interval. So what we need is we need the data. So you can see all this data right here. Now, interestingly enough, oh, Christian, that's you guys are so nice. I mean, I don't know. It's a lot going on right now, and I really appreciate you guys. Your positivity, your compliments, all that good stuff right there keeps everyone going really strong and really happy. So I'm here to help. You guys just ask questions. Email me. Please email me. For anyone being like, I don't understand what's going on. I'm stuck. Email me. We'll talk about it. Like we'll work with everybody and we try to be as understanding as possible. So, yes. So Rachel, what we're going to do right here is we're going to open a new sheet inside of here. So I'm just going to File and then New Data Table. So step number 1 was to get the data. Step number 2 is to go to Jump and then go into here. And we are just going to put our data into Jump. So we're just going to take the data and we're going to go to Edit and I'm going to paste with column names. Now here's the big thing. This is where people make a mistake. This is a huge spot where I see tons of mistakes happen. It's that people don't paste with column names. They just, yes, check those points out. They don't paste with column names. They just paste normally. If you paste normally, you'll have it. Hey, what's up, Alex? So good to see you. Alex, check it out. We've got the points working now, so you can do exclamation mark points, and you can check out your points. So good to see you, Alex. And so you can check out your points. You can see what's going on. I've got home studio right now, so you can look at your points. I've got polls and all this stuff. We're working on new great things. I know, right? So good to see you here. Hope you're doing well through all this craziness. Oh, I typed 2 up here. This is incorrect anyways, though, so it's not working. And Rachel, if you're stuck at any point, tell me where you're stuck, and we'll get it fixed up. So next we see that we have right here the data is inside of here. And let's go ahead and go to Analyze Distribution. Remember, you can slow down this video, you can rewind this video, you can pause this video. So we're just going to Analyze Distribution. We're going to double click this variable to put it over here into the Y. We're going to click OK. And then we're going to click up here to Stack to make it nice and pretty. And there we go. We've got our data and we've got our view right here. So all of this is looking great and we can see what's going on. So here is the confidence interval right here. 58.4 to 46.14. Usually we read it the other way though. Oh, thank you so much. I'm so glad it's working right now. So just trying to do new fun things. And so now we go back to our answer sheet and let's go ahead and put in the data. Wrong button right there. I want to go here and then there. So the answer is 46.15. Make sure to do the 2 decimals. Always, I wish they put that in red down here because I've made a mistake. Remember, we will fix rounding issues, but it has to be close. It has to be very close. If you put in something like this right here, I would accept it. Or if you put in 1 too many decimals, I'll accept it because I know you know it. And the point isn't, I mean, yes, be accurate, but you know, I understand. I don't want you to work on an assignment and make like a 90 because you put in 1 too many decimals. I'll help you out there. So 58.42, because watch me get something wrong by rounding. 58.42 is that one right there. And remember, we should understand what this interval means. I am 95% confident. The true mean amount of time it takes these rats to run the maze is contained in the interval 46.15 seconds to 58.42 seconds. They're trying to have it be a 60-second maze, so that'll come up here later. Now, this one can be a little bit tricky because we need to look at our data. Now, the best thing to do is to make our data look identical to theirs. We see theirs starts at 20, goes to 100, has bin widths of 5. So that's 20, 25, 30, 35, 40. So we're going to double click right here. We're going to go from 20 to 100, and we're going to go bin widths of 5. So all I'm doing is looking at their number line and then figuring out how to make my number line the same. The min, the max, which is the min, the max, right there. And then the increments is the bin widths. This, I wish that just said, oh, it says bin increment. That's very close to what we would call it. And here we are. So now we look and we see we have an outlier. So it has to be this graphic or this graphic. We see kind of this slide right here like, whee, and we see this little divot. And there's the divot and there's the slide. So the answer has to be this one. Now here's where people get confused. A lot of people have forgotten what a normal probability plot is, known as a QQ plot or normal quantile plot. So when people are stuck on this right here, I always give one bit of advice. Normal probability plots always go up and to the right. So that eliminates this one, that eliminates this one, and then it brings it down to just these two. Now, a normal probability plot shows us how normal the distribution is. So you can actually look at the values of the y and figure out what's going on here. If you notice, there's this big gap in here in the values of the y. What do I mean by the y variable? We're analyzing time, so we want to see like what's going on here with the time it takes the rats to run the maze. There was this outlier here that was probably, we can see what it was. That outlier was 92.14 because it's the max. And so when we look at this right here, we can see this 92.4 right here, and there's no data going over here. Now, these down here are the z-scores, which will tell us how normal it is, because it should follow that there's kind of this pattern to it where we see most are in the middle, and then we get further out. There's fewer like at -2 and +2, because those are more extreme z-scores. This is a pretty large z-score right here. This 92, was it? Something like that. It was 92.4. This was a very large z-score, and there it is on the y-axis at 92.4, and then there's no value up here on the y-axis. This is not the 92.4. It should be up here. So the answer is C, pretty easy to tell from the outlier on the normal probability plot, and it must go up and to the right. That's the way they go. It's the way they're drawn. Are all the conditions met? Here's where the fun happens. We do have an outlier in here, so this is going to be, we're going to have to remove that outlier. So we got to look. This one mentions outlier. The only one that doesn't is this. You're eliminated. So the randomization condition is met. The normal probability plot is relatively state with one outlier. They should seem to be met. Sorry, guys. Cereal. So one question D, when we use the train function, what would it be? I'll take a look at that here, Connor, next. You got it. We'll go back and do 1D. I bet if it's quantitative, it's probably just going to be method CV, I think. If you're predicting, no, you're doing purchase. Are you doing, tell me, Connor, in the chat, AUC or accuracy? I'll show you which one it'll be if it's AUC. I think it's AUC. So I'll show that here in one moment, but I think it's AUC, and then I'll show you what the train function, what the the train function or the fit control. You're just thinking about the train function? I'll check it out in a moment here. So my brain broke. Without the outlier, the condition seems to be met. The histogram is roughly unimodal and symmetric with no outliers. Yeah, and so this looks to be right here. It's roughly unimodal and symmetric. I know it might look to have a little bit of bimodality. Yeah, I believe GLM. Yep, that sounds about right. I'll take a look here in a second because that'll do logistic for you. So I think you're doing logistic, and so GLM will work on that. So yep. And so the randomization is met. The histogram is bimodal. Nope. The randomization condition is met. The normal probability plot is not straight. Without the outlier, the histogram is nearly unimodal and skewed to the right. So it's roughly symmetric, and that's kind of what we want. Yep, AUC is one of them. Accuracy and AUC would be the two. And so good job, Connor. Awesome work in the chat right there. So if you look at this, the normal probability plot is relatively good. Bin widths can change, and so this is where I know this is the weird question, I think, for a lot of people, is because if I change the bin widths here, then now it looks pretty much unimodal. I know there's a gap right here, but especially right here, that's unimodal with just the one outlier. So it's hard to tell its exact shape. That looks still kind of unimodal. It's like that especially looks unimodal. So, and I'm just changing bin widths right there. Oops, don't want to get the wrong answer. So it's pretty much unimodal with one outlier. And so now we're going to eliminate that outlier. And let's go back, eliminate the outlier. You can do that by clicking on it. We're going to click on it. So Max should have the toolbar up top, I believe. And you can just click on it. And here's what we're going to do. We're going to do this in one step right now by going here to rows and hide and exclude. So when you do hide and exclude, it won't change your output over here. You have to go to the red arrow and go to redo analysis. If you notice, now we get an output without the point in here. Whoops. I think I heard someone talking about that lately, where you can shake it and everything goes away. So we go right here, and here's the output without it. Please notice that there's 20 observations here, and in this one there's 21. So keep your graphics straight, don't get them mixed up. 21 observations, 20 observations, and let me pull back up the chat and everything, there we go. So we're gonna go over here, the 20 observations, and we can see 45.54 and 55. 45.54 and 55. Now it never hurts, once again, to make sure that you put all your numbers in the right way, because 45.54, 55, just don't get them wrong. Does it meet the 1 minute requirement? I'd reject that value because it's outside the interval. So it does not meet the 1 minute requirement. I would reject the interval. The maze does not meet the 1 minute requirement. Both intervals are entirely above. Nope. The maze does not meet it. Oh, it meets it. No. The maze does not meet it. Both intervals contain it. Nope. The maze does not meet it. Both confidence intervals are entirely below a mean of 60 seconds. The maze meets. No. It does not meet it. They're both below. Let's give it a check. 87.5. What did I do? So did I click one of my answers wrong? Oh, no, that's not fair. That's when I was clicking around. We said, hey, Tyler, good to see you. That's not fair. I didn't get that wrong. For anyone watching that's not fair. Make sure you don't off-click an answer. But I was like, I swear, I took my time on this. I did say this a bunch of times. This is the right answer. I want to review that tape, and I want to see where. So for anyone, Tyler, you didn't see that. I misclicked, apparently, but I did say it about 10 times that this is the answer due to the point right here in this plot. But my clicking around caused an error, and somehow this got clicked. So that is not the right answer, because I kept pointing out 92.4, which is the maximum of the data set, is not there. So I know, I can't be wrong. No, I have made mistakes on these before, but that was a misclick. Somehow I must have clicked like, yeah, you see, I bet that's what happened. That's so weird. You can click over here, and you see if you click over here, you'll select the graphic. So I must have somehow, when I was clicking back between pages, man, that's a bummer. I'd hate for that to happen to someone, but things like that can happen. That's just user error. You understand the concept, and then an error like that happens. So once again, the answer is not D right there. So and we got Connor's got some code in the chat. So this looks to be correct right here, Connor. How's that running? Thank you so much. You've been you're welcome, Rachel. Were you able to get it right, Rachel? Does it make sense right now? Feel free to ask any questions if you have it. I'm gonna do this one real quick. Connor, that looks 100% right. Method GLF, yep, pre-proc center scale. Is everything there running? Looks to be 100% right. See, I'm trying to think of the easiest way to get this into R. So we could go to, I can copy it, and I wish there was a quicker way to paste. How do you show the best three? So you want to show the best three models, do you? That's what you want to show, your best three models. Let me look at that in the homework. So this is D, is it? Right here. Are you going to look through your results? Are you trying to check the sanity check right here? Are you trying to check which best three are you looking at right here? Last three numbers in the best row. Yeah, it should be, and hopefully I swear, sanity checks are working. Yeah. Go back to the video, and if you have more questions, feel free to ask Rachel. If you're like, how'd you do this? And I'll answer anything. So these right here, when you run this, and so we've got here the fit control, and I should be able to take, let me take your code right here. We'll see what the sanity check says from me today. I like how when you copy stuff, sometimes you get that weird thing right there. So purchase not found. So let's see. Oh, and I haven't changed the variables. So, well, what you should be able to do, purchase not found. Oh, because I haven't made train yet. So I have to make my train data. So we'll go right here. I'm just going to kind of do this. Would you mind explaining AUC? Yeah, we'll do that next here. Good question on AUC. And I know how that one relates. A lot of people have been asking that one via email. So we want to take, I'll make train rows. This is not going to be the exact same thing right here. So I'll use that. Here, wait, Connor. Retract that message, Connor. So that way it's not, someone's going to be like, Brian, no. So retract that method. Yeah, thank you. Wait, and I don't have train rows. Okay, wait. What's going on with all my code right here? Okay. So set seed, train rows. Something's going on weird right here. Set seed, unexpected symbol. So let's see. Okay, wait. I think that's the issue. And that should go there. Okay. That looks to be unexpected symbol in train rows. So let's see what's going on here. Train rows. Let's see. No, it's all right, Connor. Don't worry. Someone's gonna be like, dang it, Brian. So they're watching the video right now. 1 through n row. What is going on right here, Connor? Why doesn't it like it? I've seen this when you try to copy code in sometimes. Semi after set. Oh my gosh, you're right. Connor, 1,000,000 points. Yep. There. And did that not? I wonder if that didn't copy over. Unexpected symbol. So there we go. We'll just do that. There we go. Okay, cool. That works now. So what it was, Connor pointed out that he had 2 lines of code right here, and I think the semicolons didn't copy paste or something. It's weird. I've seen that before when you try to copy paste between things. R will just like not take everything you want. I don't know why. It happens. We've got here the fit control is set up. Awesome. So what we should be able to do, accuracy, that's awesome. We should be able to, you could call this train. Yeah, I'd probably call this like GLM. I'd probably call it that. That makes a little more sense to me, because this is a model. And so we should be able to go to the results right here. And we only have this one result right here. And is that what you're getting, Connor? Are those the numbers you're getting? These look very familiar to me. What are you seeing for your last few numbers and everything? How do your numbers look? And for anyone watching this video, I'm very sorry. I'm gonna make sure the graders know to check like your work. The numbers might be a little bit different. It's just with all the randomness updates and everything, I don't know if they're, I swear we try to keep the things as consistent as possible with sanity checks, and then somehow something changes or something. But what are you seeing for your last few numbers? It's specifically talking about these right here, these last 3 numbers, and we're seeing very, very, very different numbers on this sanity check right now. So I don't know what you got, because I did it kind of quickly, so I'm hoping, but everything here looks to be accurate on the theory of what we're doing. Then we'll talk about ROC next. But I'm going to be informing the graders to be as nice as possible with, like, be looking to see if they did the work properly. The numbers might be different. Mine match up. I was just being oof. Oh wait, do yours match up with this right here? Do yours match up with mine down here at the bottom, or the actual sanity? Which one? Wait, sorry, I'm asking 2 questions. Mine or the sanity check? Which one does it match up with? Yours match with okay, then why do mine not match? I swear I'm running all the same code, and this is the weirdness we see. You know what it might be, Connor? What version of R are you running? And I think this is it. I think this is the problem right here, and this is what we have to watch out for. Set seed again. Okay, and you've put the set seed where before it? So, yeah, remember to set seed. Da, da, da. Okay, here we go. Let's put set seed before it. Let's see what we get. Let's see if it does it. Boom. And I could check my holdout too. Nope. That's a nope on that. Let's look to see if my holdout is the right thing. So we want the right holdout right here. Okay, that's right. That's correct right here. After fit control. Yeah, so right here, we've gone after the fit control. Let's make this look a little bit nicer right here. Okay. And then we can make this look a little bit nicer. Let's go right here. Okay, cool. So a little bit easier to look at. Yeah, that's probably it. And so that's the thing is like I have the right, if you look at this right here, and this is why, please tell, for everyone watching this, yeah, and then Christian, are you getting, this is the crazy, so Connor's getting it, and then you and I, Christian, are not getting it, and I think, Christian, I emailed and talked to you about this yesterday, I think you're using 3.6.2, and then Connor's using 3.6.1, and then I'm using 3.6.3, which is why we try to put everyone to the same one. It's just that I recently put R, like, re-updated on this computer, because I don't, like, my goal was never to use this computer for R a whole bunch, but now I use it a lot more for R. So I updated it, and yeah, so what we see right here is that this one passes the sanity check. It's exactly what we would get. I'm a bit off date. Yeah, that's all right. It's just tell us if anything's weird with the grading. We'll fix it. And then we have 2019 right here, and when I run this, I don't get the sanity check, which is weird. You would think I'd get the sanity check, but I think it's 3.6. Maybe it's 3.6.1 is the one you need to be using. I don't know. I'm sorry, guys. It's the hardest thing is that we're trying to control randomness, which is like trying to control. You went over the flight for the confidence intervals for the mean. I can do that one next, I think. And Connor, keep coming with more questions. So you should be all right, Connor. Here's the cool elastic net stuff. And really all you're going to do is just change your tune grid. Yeah, I think that's it. That we did updates to this like last semester, and then this is why it's being, yeah, maybe that's why. So once again, I'm going to be telling the graders, and please tell us if anything's weird on the grading. Look over your assignments. But I think that's it. And Rachel, we can do that question right here. Let's do the flight one, and then keep coming up with questions, Connor. So good to see everyone here. I love all the questions. This is my redemption right now. Was it like Thursday? Here we go. Thursday I did like a ton of problems and I got all of them right, so I love that. It's just so easy to make a mistake on these. It's so easy to click the wrong button. We just saw that earlier. But this one, we're going in and we're going to get 100. Hey, what's up, Joel? We were just doing some 474, but ask some questions and we'll put it next in the queue because right now I'm going to do the flight question and then we have free open space. But I started the video talking about 474, did about 30 minutes. Connor came in, we did some questions there, but keep asking questions. So good to see you in the chat. And let's go here. This one gives us notation, so we're gonna have to take that notation and make sure we know how to write this down. So basically gives us it, but there's one other thing we need that it didn't give us. So, and there's, Connor wants me to do AUC ROC, which I was talking about earlier, but we're going to talk about it again. So with this right here, can you review why? Yeah, we'll do that next because Connor was wondering about that too. So here we are. And when I see N, Rachel, if you're watching, what can we get from N? What can we get from N? That's the big question. If we're making a T interval, then one sample T interval, oh, good to see you, Christian. I'll see you tomorrow. Degrees of freedom equals n minus 1. So we need to know that the degrees of freedom for this problem are equal to 71. Now, as soon as I see the degrees of freedom in a problem, here's what I do. Every time I see degrees of freedom, I go to the t-applet. So I go to the t-applet, and I say, okay, let me go to my t-applet and get the proper t I need. This is especially true for confidence intervals, and I'll put this in the chat, but one of my favorite websites is this one right here, Stat Distributions. Really good website for getting your T's. And so we'll go here to the chat. We'll make sure we copy paste, grab everything, copy paste, and put it in the chat right there. And this is the website I use. So we have 71 degrees of freedom. Do you have a video over chapter 14? Yeah, here we can do that next too, Caleb, if you want. Yeah, I know I'll probably change it over and make this one. I think it's just so easy visual to see. And I think they've changed the decimal places so that it's easier to use this one. And we want, it will eventually do a confidence interval, so we'll see here in a second what confidence interval it wants. Is the independence condition met? There's no evidence of a trend. Yes. Independence condition met. Is it random? Yes. Now, be careful on these because it'll switch where yes and no is at. I see a lot of people miss these because people think yes is the first one. I don't know why. Look, I bet you, nope. It kept them all in the same spot, but it does randomize them. I just got lucky and they're all in the same spot. But watch out, yes and no can switch spots. I've seen that in this question. Is the 10% condition met? Yes. 72 flights are less than 10% of all flights. That's what that condition is. Is the nearly normal condition met yet? Yes, because this is basically unimodal and symmetric. Yes, that is a little bit of an outlier, but it's pretty unimodal symmetric with few to no outliers. So really good. Sample size is large, so we could use large enough n because we see here that it's pretty normal, for 72 sample size, we're good. Not to reteach that whole topic again right here. Make a 90% confidence interval. Oh, 90%. So you have to go over here to the site. We already have 71 degrees of freedom. Now you could do it with this. You could put 10% on the outside because 10% on the outside is 90% on the inside, but we can go right here and do 90% on the inside. This is the way I like to display. It's the same number right here, but I like to display them this way because a confidence interval is the inside portion. I usually use this for a two-tailed test when I get the t-value. Like if I got a t of 2.4, this would tell me the p-value for a two-tailed test. And even though this says p-value, you can use it for a confidence interval right here. I wish that just said area. Now I'm doing a 10% confidence interval. There's a 90% confidence interval. And you can tell it has a larger t, which makes it wider. So we're good to go on this t-score right here. We've got it 1.667. And let's hop back over here. And I believe, I might look at something really quickly right here. So that's the t-score. And, well, let me write down my equation first. So with everything I have right here, I need to write out my equation. Y bar plus or minus t star with n minus 1 degrees of freedom s over square root of n. Now we're going to go right here and do y bar of 80.4306 plus or minus 1.667, and then 2.81839 over square root of 72. There we go right there. And that is the full equation, just taking into account all the notation. If you notice, this is y bar is the sample mean, and then we have the standard deviation, we have the sample size, and we have the degrees of freedom. Now the degrees of freedom don't get multiplied, they're just used to go to the t-distribution and tell you the t-score related to those degrees of freedom. So there's a calculation middle thing. You use them to get the t-score. The star right here means you get to pick the t. Now the question picked the t, but it could have been a 95, could have been a 99, any of those right there. Yes, and well, the z table we will use for z's, and then the t table we will use for t's. And then David M. Lane is super awesome. This side right here also has the normal curve on it. And my absolute favorite, I'll show you guys my favorite, but it's more complicated. We have the Iowa applet. And so the Iowa T applet is absolutely amazing because it carries with it more degrees, or it carries with it more decimal places. It's a little more complicated to use because it's more mathematical. But so this one is 1.6666. So there's a few more decimals on it. And maybe I'll put this one in the chat too. But this one is like, this is the super advanced T applet. So this is like the probability statement, as in, I do not understand, Connor. Explain more. But this one right here is the way advanced. It gets like really accurate answers. And so I think this is accurate enough, 3 decimal places, let's hope, but we should be all right. That's why the other applet, it's like, it has such a nice user interface. That's why I like it. So this one, yeah. So let's go 72, square root it. I'm just doing the bottom of the equation. Copy that, 2.81839, carry all decimals. Divide that by that. Now that is the standard error. All I've solved is this part right in here. So I've solved this part of the equation. And now I'm going to multiply that by 1.667. Now when I do that, that makes this whole thing here the margin of error. So I've now solved, yep, that's the way they've had it written exactly. We're going to solve the margin of error right here, 0.5536, so 0.5537. So, oops, we're in highlighter. .5537. So that's got it right here. That is the, we're going to copy this right here. That is the interval. I'm carrying all the decimals, why not, for the moment. And we're going to go back to our answers. I just need to solve this as I do my problem. And the numbers are on the screen, or at least the number I need up there. Now be very careful, because we have our margin of error saved in our calculator. So we're just copying it to make sure it's saved. Control-C, Command-C. And then we're going to go here. That's Mac versus PC. We're going to type this very carefully. We're going to go plus, put this in, 80.98. And then we're going to go right here and take 80.4036, subtract that, 79.88. And it's a pretty small interval, isn't it? Yeah, it's probably a pretty small interval. And so we go right here. You know what I might try to do? I think, Connor, I think there's a way to do this on, let me look inside of R real quick, because I want to check it with R if I can, because why not? And then we're going to talk Joel and Connor's question on, so t-test, there's t-test. And let me see if there's a way to use summary statistics on this. Because I wish it would let me just input summary statistics. So we've got right here, there's the value you're testing. I could do it inside of here and have it check it. But yeah, you can only do it that way. What I could do is I could write it out really quickly. Let's just solve it in here. Because what I want is QT. So good, there's that. So if you notice, this is the t-score we found. And so we're going to go here and create an interval of this. We're just doing inside of R real quick. And then, so I can actually make a function that does this. There's already at least one package at CRAN which does the summary statistics of the t-test. See the function t-sum test in package Connor, you are amazing. Let's check that out. So install.packages right here, and then BSDA. There we go. And then Connor, 1,000,000 points. So Stack Over, yeah, Stack. I literally was helping out my brother with Stack Overflow. He had some coding questions, and I was like, "Let's go." And he was like, "Stack Overflow," and I was like, "Yes, this is the site. this is the coding site." Oh, library. See, why write a function when someone's already written it for you? Right? I was gonna write that into a function, but I mean, it's good to know how to write functions, but someone's already done it. So tsum takes the mean and the standard deviation and the sample size, and then it can do a 2 sample if needed. Okay, so it looks like performs a 1, a 2 sample, or Welch's, all this good stuff. Wow. So the first thing it takes is mean, standard deviation, and sample size. Wow. Okay, so it just takes the summary statistics. So all we need to do is go back to here, and we take the mean of 80 point. Can I copy those? Of course not, right? So we can just go up and down like this now. There we go. 80.4306. And standard deviation of 2.81839. 2.81839. Sample size 72. Run it. Var equals ignored for 1 sample t. So yeah, it's not doing equal variance. Let's see right here. Did do it the same way. 79.88. I wonder which way it's calculating. We're getting slightly different answers right here. T equals this. Oh, it did a t-test on it too. Oh, it did 95. That's why we're getting the different answers. So we wanted 90%. So is it conf? Yeah, there we go. Thank you for making it very easy to figure out what the 80.98. Yep, 87.88, which I think is exactly what we got in the calculator. If you look at how decimal place precision close we are to what the exact finding is, and so it scared me for a moment until I saw that it was a 90% confidence interval, and then I kind of guessed that it would be conf for the next argument. So it's pretty easy to figure out how to work these things if you know how arguments work. Like, oh, I need to add in one more argument to change the confidence level, and then you can go right here and you can just make whatever interval you want it to make. And you can see that's going to be a wider interval, and this is going to be a shorter interval. And as long as we've been entering in numbers the right way, then we have confirmed that this is the right answer. Connor, nice work. Let's make sure we don't click a wrong answer like I did last time. We can be 90% confident this sounds about right, that the interval contains the true mean monthly percentage of on-time departures. We're going to cross our fingers. We're going to hit enter. Of course, we got 100. Boom, we got it. Woo, I'm always scared, but you never know. So great work, but knowing how to do things like this is very important. If you notice how easy it makes it. Rachel, awesome job. And so I always like showing off the coding, Rachel, if I can to 201ers, because if you notice, with especially this function right here that someone already wrote for us, it made it very easy to where we could literally just say, like, if we wanted a 95. Now, the big thing I want to point out is if you notice here, 1,000,000 point question, 201 or 320 or 474 can get this, but what is that t right there? That's not the t of 1.666 that we found. Why is that t what it is? That's a huge question. Why is that t what it is? Any ideas, like, what is going on with that t? That t does not change when I change the confidence level, which you would think the t would change. There's a reason it's not changing. Why is this t the way it is? What does this t mean, and what is it doing? What is that t right there? I bet you the other argument is this. Is it that? It is that. It is that. This t right here is the t-test. This is the t-test. And this is the hypothesized mean that I'm entering in. So I could put my hypothesized mean to this right here, and now I'll get a t of 0. So my t is 0 because I hypothesized the sample mean to be the true mean. And now the p-value is 1. So lots going on right here, but this is doing a t-test. So this will do a t-test and make a confidence interval. Now if you notice, here's something I want to point out. I'm going to put this right at the edge of this. This is right at the edge of a 90% confidence interval. This goes back to 201 right here. Really good thing. Does anyone in 474, this is my last question, does anyone know what the p-value on this test will be? Does anyone know what the p-value on this test will be? This is really good concepts of how tests and confidence intervals work, because this is right at the edge of a 90% confidence interval, and this is doing a does not equals alternative, which kind of coincides with the confidence interval. So what will the p-value on this test be? This could literally be a 2-1 question. So it's right on the edge of a 90% confidence interval. Well, no, it was 1 for the previous one, but since this is on the edge of a 90% confidence interval, if it's got 90% inside, that's the answer. It'll have 10% outside. Because the value I tested, and look at the t-score now, the t-score is the t-score we were getting because this is right on the edge of a 90% confidence interval. You could do the same thing with a 95% confidence interval, find the edge of it, and if we were to take the lower bound of this 95% confidence interval, the p-value will now change to 5%. So the p-value up here is now 5%, and we actually get the t-score for a 95% confidence interval. So it's because 95, if you're right on the edge of it, it would reflect it to the other side of it, and you'd get 5% outside. This is how confidence intervals in tests can be used to do the same thing. So it's kind of good theory, like, what does that t mean up there? And that is actually the t for a 95% confidence interval right now. Yeah, mu is on the edge of it. Mu is the value tested, and let me write the formula real quick, real good practice, especially to help people with kind of excellent work. And don't worry, I've been teaching this for years, so that's how I know these things. This one right here that we're doing to get the t is this. Let me write it out the right way. What we're doing right now is t with n-1 degrees freedom. This does not get a star right now because we're not going to pick this. We are going to solve for this. Technically, we can pick mu. In this example, you would pick mu. So let's point this out. This is huge for 201. When you make, and I've seen a lot of people make this error, it's a very common error, that when you make a confidence interval, everyone knows you get to pick t. But when you're doing a hypothesis test, you're picking what you hypothesize. So you don't pick your t for a test. You pick your t when you make an interval. More just, about Zoom. So you guys are so awesome. I'm so glad our 474 class, I feel like it's such a good community. Like, I see everyone talking to each other. Like, I feel like you guys are so inclusive, and I love that about it. Like, man, and I didn't get to teach 320 this semester, so I can't, like, bring up the students, and, like, I get emails from students, hey, I've heard about you, and I'm like, dang it, I haven't had you in class. So you guys, I'll be teaching 320 again next semester, but I like teaching 320 because then I get to meet a lot of the business analytics students, and we'll start talking about AUC, ROC, and why the bank would want to use AUC right here. So Joel, so great to have you here, and I can tell you where you guys sat in class in 320. Connor sat, and don't worry, like, Connor, like, I know where he's at. Like, he's at, right there, I look right towards, like, in the middle. Just boom, all the way. There we go. And then Joel right there, front, to the right, 2 seats over, and Connor right in the middle, right there in the back. So I can see you guys in class in 320. I can see most of that room still. Yep. And so, but you guys always interacted, like, no matter where you guys sat. And so you guys are amazing students doing an amazing job. So thank you both for, like, working so hard. And I just, yeah, I know, right? I like that room a lot for teaching because it's got that long aisleway. It's probably my favorite room because I've taught a lot in that room. I'm very accustomed to it, and it's like, it's so close to when you walk in. Like, I could go down the elevator, walk in the door, remembering being on campus again. I could go down the elevator, go in the door, and be in there in a second. So that's probably my favorite room in Haslam to teach in. Such a good room, such a good building. We'll be back there again soon enough. If you guys probably saw, here's the biggest thing. Let me bring this up real briefly here. And everyone's probably all like, COVID-19. And then we'll talk AUC real quick. Let me go back over here. I think, let me see here. This is why, where is it? Can I find the model? Does anyone know where those models, is this the right one? Yes. Oh, good. Wow, the model has changed, and I like that. Ooh, that is it's got a bimodal. That's interesting. Okay, let's bring this over to here, and let's talk about what's going on with these models, because we just talked in 201 about confidence intervals. That's what this is. I'm in 201, what's T? I see the example for the chapter 14 for the mean. I need, yes, let me show you that real quick right here. You want to go to, let me find it for you right here. I'm going to send you the site to go to. So you want to go to stat distributions, and tell me if you're stuck on this. Talk to me in the chat here if you're stuck on this. I'm going to send you the site. So Caleb, you want to go to this site right here, and you want to put in your data. So let me show you. You'll go right here. You'll enter the degrees of freedom. So the degrees of freedom you'll enter in will be like 71 degrees of freedom. Then I usually use this one right here, and you can then enter in like a 99% confidence interval, 98, 97, 90, whatever it is. Hopefully I'm not blocking that right there. But you can grab the t-score right here that you will use to make your confidence interval by entering in the degrees of freedom. And be careful, sometimes if you change one of these, it'll change like the numbers. So be very careful. Make sure it says something like 90 right here. Usually I enter in the degrees of freedom first, and then I put in the p-value. Now it does say p-value, but that is the amount of area shaded. So Caleb, say hey in the chat if you're stuck, and awesome work there, Caleb. But with these graphics, because I think this is so important right here, these are all confidence intervals right here. So I would assume they're 95% confidence intervals, and we did have 2 good days of good numbers, but we have seen where we have had good days. So we like good number days. That's what we like. We like good number days. But everything you're seeing right here is confidence intervals. Like look at this plus or minus. I wish I could hover over it, but if I move it, it doesn't hover. It just moves the graphic. But you've got confidence intervals on everything going on right here. That's why understanding that, we are, we might go down, it'd be great. But here's the thing too. So we might not, I hope we go towards the low end, and I hope we go outside of these. We're not saying that this will happen, but we are 95% confident that the true DES per day, fun topic, will be contained in these intervals. So we're 95% confident the true DES per day is this today? I am 95% confident the true deaths today for COVID-19 is contained in the interval 1,166 to 2,775. And then this is the estimate, which is the center of the interval, is 1,745. And it's today, April 5th. Today's April 6th. Someone should yell at me in the chat. No one can track time anymore. And here is the estimate for today. Here's the estimates for today. But this is why confidence intervals are so important. One thing I want to point out is that the confidence intervals actually get way wider when you go out here, because this is a very uncertain point at the peak of the curve. And we do see that the estimates are getting so small here that there's very little variation. Probably due to the lack of variation, the curve's getting smaller there. But the further out you go, the wider it usually goes, and there's more uncertainty further away, and there's probably more variation. And these are going off of a lot of medical models or a lot of immunology models on how things work out. So really interesting stuff. And let's talk about that AUC thing right here. But you guys are awesome. So let's do this right here. Let's hop over to AUC and let's do this. Okay, so the question is, why would the bank use AUC? And so with this right here, AUC, let's do it. So with AUC, what is the goal of AUC? What is the goal of AUC? So in the goal of AUC, it's about getting your true positives first. And I always like using my sister as the example, because if she's going to market to people and she has a list of tons and tons and tons and tons and tons of customers, like 10,000 people in Knoxville she could market to, well, she might have a model that has 80% accuracy. So 80% accuracy would mean when that model makes a prediction, it's correct 80% of the time. Like, it's going to tell her that someone will purchase and they will purchase, or they won't purchase and they won't purchase 80% of the time. Its prediction is accurate 80% of the time. But when we look at this, when we look at AUC, what does an AUC of 80% mean? An AUC of 80% means that the yes case, what? Can anyone interpret what an AUC of 80% means? A million points in the chat. I'm just going to give it a moment. The yes case receives a blank this. So what would it mean to have an AUC of 80%? Who knows in the chat? The yes case, because that's what we're predicting. We're trying to... Awesome, Caleb. Amazing work there. And whenever you're stuck, just ask a question. I'll put it in the queue, and we'll keep doing that. When I waited tables, I'd always talk about my queue, because I'd be like, okay, fill drinks, run food, put ice in the ice bins, make tea. I remember all the tasks. Sweep floor, wash hands, like all these cues. Now you wash hands. Put ice in, wash hands, grab food, wash hands. So the big thing, great question, Joel, is that what AUC means is how we rank each one of these. Yes. Well, that's more like accuracy. Kind of. It's the yes class receives a higher probability than the no class 80% of the time. The yes class receives a higher probability than the no class 80% of the time. Our goal with AUC is that if we were to look at the way these things are ranked, we would want them to put all the yeses up top. What you want is something like this. This is where Joel's talking about where I write all the yeses and the nos, because even though, let's do something like this right here. Does this model have 100% accuracy? Is this model 100% accurate? Yes or no? Is this model 100% accurate? Yes or no? And think about, we're predicting yes. So is this model 100% accurate? No, this model is not 100% accurate because of this right here. But this model would have an AUC of 1 because the yes class always receives a higher probability than the no class. So if you were going through a list of people, you would not catch this yes person right here. This is just one example where AUC is going to win out because the AUC of this model is 1 because the yes class always receives a higher probability than the no class. Does that make sense right there? In this example, the yes class always receives a higher probability than the no class. Like you would do all pairwise comparisons. You would compare this yes to these no's, and that's 100% higher. You'd compare yes to these no's, that's 100% higher. And you compare yes to these no's, pairwise comparisons. So you're doing the pairwise comparisons of all the yes to all the no's. But the reason that this has an error when it comes to accuracy is this one. This model is only 80% accurate. Yeah, it really depends. A bad AUC is 50%, because then that would be 50% of the time the yes class receives a higher probability than the no class, which is pretty much the naive model. Because the naive model, or not even really the naive, because the naive might predict everything to be yes or no, and then the naive might be 80% accurate. Well, then it would give everything an 80% probability. Yeah, the naive would not have a really good AUC. So what you want, and this is where we get into the drawing of AUC, we draw this graphic right here. What you want is when you move through your data, and when I'm talking about moving through your data, I'm talking about when you move through your data like this, when you move through your data like this, when you move through your data like this. Moving through your data means you're actually looking at the observations. Is there ever a case where accuracy is preferred? I would say so, actually. Joel, great question. Accuracy might be able to be used, or there could be a good case for accuracy made because of the utility of its understanding. So if you really have to communicate your model, you're going for a very descriptive model, you might just say the accuracy of it. Now, I would probably still use AUC. You could tune a model on AUC and you could tune a model on accuracy, and then you could see which one does better, because you're really it's like baking a cake in 2 different ovens. Now imagine someone has like a new super awesome oven and it's got all these like temperature controls on it. You could bake it in that oven, or you could bake it in like your old traditional oven, and someone might be like, well, there are people who like that old traditional oven, and there's people who like accuracy. Accuracy is a much easier thing to understand. It's not as complicated. So accuracy is your old traditional oven. It works. It's fine. It's a good thing. People understand it. It's just got the knob that you turn the heat on. That's it. And then this newfangled oven that's got all these like moisture control, humidity control, all these things. You have to explain it. It's a lot. It's probably going to make the cake better, but some people might just be like, I don't understand that. Now what you could do is you could just bake the cake in that oven and not tell anybody and say you made the cake. But if someone really wants to understand, they might be like, that's too complicated. Just use accuracy. Does that kind of make sense? It's why we teach both, because accuracy is very important to know. I mean, obviously what's going on. Can you give another example? I kind of understand the one about your sister, but not 100%. Yeah. So what it is, let me try to give another example here, is let's say I want to predict, I want to do more with students, like to help them, because one of the hardest things for me is like when someone kind of can't find success in college. And I know that probably happens more than we'd like to think, but someone gets to college, just can't find the right ways to study, can't find the right, just pace for them in college. So what I'd like to do is make models that predict if somebody is going to drop out of college. And of course, for some people, that's a very viable option. Maybe it just doesn't work for them. But we would assume when people drop out of college, especially if they're in their junior or senior year, that probably something happened like financial hardships, things that we would want to hopefully mitigate or help them have a better way of, like so they can finish college. So we would make a model here predicting if somebody's going to drop out. Does that all make sense? We're going to make a model predicting if someone's going to drop out. So the accuracy of the model would be correctly predicting those who drop out and correctly predicting those who don't drop out. So that's the accuracy. But when we look at AUC, now imagine this. We have limited resources on what we're going to use right here. We are going to try to find like 50 students, and we're going to meet with them and give them like this personal help. So think about how big UT is, 20, 30,000 students, and we're going to have 50 students who we're going to focus on and make this initiative where we're going to help them not drop out of college. And we're going to kind of identify them early. We're going to find them their freshman year. We're going to start this and we're also going to identify, no, actually, here's what we're going to do. We're going to make this totally awesome. We're going to take a sample size of 100 students that we identify as the most likely to drop out of college. Does that make sense right here? These are the students who are most likely to not finish college. And yep, an experiment, total experiment. And then this is what we're going to do, is we're going to make random group 1, random group 2. And this is the kind of sad fact of it, but we do have limited resources. So from the total size of our sample, we're going to make 2 groups, one of size 50, one of size 50, same sample size here. And this is our control group here. I mean, it is kind of sad, but we're just going to monitor them. We're going to give them no intervention in the control group, kind of blocking that 50 right now. There it is over there. So we're going to give the control group no intervention. We're just going to let them live their college life normally, even though of course, if they reach for help, we're just going to let them be a student like we would any other student. Does that make sense? Because we're going to show UT, like, here's what we have normally going on right now. Now, if UT has other measures in place, which they contact them, that'd be awesome. But we're setting up this new way that we want to get more funding towards, because we only have, you could say, well, why don't we just reach every student? Well, it'd be really tough. And then could we give them the same level of care, the same attention, the same things? Like maybe we do some sort of like Saturday events for these students where we, bring them in for pizza and we have a speaker. We have to book rooms for these things. We have to order pizzas. So it'd be really hard to do it for like 2,000, 3,000, 5,000 students. There's a capacity. So we want to show this works so we can get more funding. That's our goal, because it's this tough things about experiments. It's like, obviously we care for these 50 students, but we're kind of saying, here's what's going on right now with these 50 students. Here's what's happening now. And then over here, and I can almost reach over there. I can almost reach the other one. Sorry, I want the screen to be perfect. One of these days will be perfect. But here's the students we're going to do something special towards. Like we're going to try to do this new program. And then we're going to show over the course of their career. It's like a longitudinal study. We're going to show over the course of their career and maybe after how this impacts them. We might even come back for like a 10-year follow-up, because we're going to always try to be, if this is working, we're going to show how it is working. And that's our goal, is if it works, let's show it works, and let's show it's a good investment. We understand it. So here's the biggest thing. If we go for accuracy and we tune on accuracy, if we make our model so it works on accuracy, all it will try to do is give us the best model that accurately puts students in the yes and no groups. But if we tune on AUC, it'll try to sort it based on the whats. It'll try to sort their dropping out based on their whats. It'll try to sort it based on their whats. Huge thing right here for this. AUC really focuses in on the whats that these students are given. Not just the yes and the no's, but the whats. Because we have another thing in logistic and all these models that we give something to make our prediction with. It'll focus very much in on this. It'll focus very, very much in on this. This is a huge thing it focuses in on, because the probabilities, exactly. It's going to focus in on those probabilities and think about how we're going to select these 100 students. What 100 students would you take if you were going to pick 100 students out of the 5,000 incoming students? We're going to take 100 students out of the 5,000 incoming students. I think that might be a class size. I don't know, 6,000. So out of the 5,000 incoming students, which ones are we going to take? Not at random. I know that would make sense. Highest risk, Joel, you're right. We're going to take the highest risk of dropping out, the highest probabilities, because the AUC is going to sort them such that it's going to try to make the model, especially when it makes it on the training and the validation, because we're going to take characteristics of people when they entered, and then we're going to see if it can predict if they drop out. So we're going to take like, okay, this student comes from this background, this family, these different things, this high school GPA, they played these sports. We're going to take everything we can take into account about them, and then we're going to see who's the most at risk of dropping out, and then we are then going to would the risk be determined by historical data or dropout? Yeah, we would take, our model would be trained on, we'd take maybe 20,000 students we have data on, let's say we have data on them, and we take all these characteristics, and then we already know the answer for them. Does that make sense? We already know the answer for these 20,000 students that we have data on. And then we see if our model works on a new set of 10,000 students who are like last year's students, or I guess 5,000 students. So we have 5,000 students that are going to be our holdout, and we're going to see if it works on last year's students. And then if it works on last year's students and can, well, I guess we need 4 years of it. So if it works on the students from 4 years ago, that's going to be our holdout because we need to see if they actually dropped out. If it works on our students from 4 years ago, then what would we do? We would assume that it works. We would assume we have good evidence because now, okay, it worked on the students from 4 years ago. That's our holdout. Now we would have good evidence that it would work on the students now, because maybe it accurately predicts who would drop out from the students who came into school 4 years ago. If it accurately predicts them, then we'd have good evidence it would work on new data. So the holdout is used to show this model was not created on this data. Does that make sense right there? This model was not created on this data. It actually works on new data. That's the key right there. So we train our model on like 10 years of historic data on students from the past. Then we use a holdout of students who came here 4 years ago, because that's kind of our most recent data, because we want to make sure the model hasn't changed. Like maybe there's new characteristics that change kind of why students would drop out. So we show that it works on new data. And then once it works on new data, we use it on the new data, because we won't know how it works on the new data till, well, actually, since we're intervening on it, we'd have to see if the 50 students we didn't intervene on looked normal. Like normal as in if they follow the pattern of what we'd expect, our model predicts. And the model predicts they're all going to drop out. The model says these 50 students are super likely to drop out that you're doing nothing to, or nothing beyond the normal. Like there's still One Stop, there's still Student Success Center, there's still all these great things we have, but the truth of the matter is we do have students who drop out, and a lot of times we want to help them out, and that's our goal. So with everything we have in place, does that all make sense? So then the model would use the AUC to determine their probabilities of dropping out. That function is semi-ranking via probabilities. Yeah, it's going to try to accurately, that's what the AUC is doing. It's trying to give the yes class a higher probability than the no class. So AUC would be really, really damaged. What's going to damage AUC the most? The absolute most damaging thing to AUC is when this no class gets a probability of like 99. That would ridiculously damage the AUC right here. So the AUC right here is ridiculously damaged, but, and I'm just writing in quick probabilities here, the accuracy of this model, good, there's 6 of them. What is the accuracy of this model right here? What is the accuracy of this model? The accuracy of this model is 83.33%, because it only gets one thing wrong. But the AUC of this model is really bad. So, yep, don't worry. The accuracy of this model is really good. It's 83.33%. But when you look at this, I think the AUC is 66%. Because if you look at it, there's all of these, when you do pairwise comparisons, every single yes class, does it make sense that when you do pairwise comparisons here, the yes class, no matter which yes class, because they're all sandwiched there in the middle, the yes class receives, I want someone to interpret the AUC, since the AUC is 66%. Yeah, exactly. So since the AUC here is 66%, what would that mean? What would that mean that the AUC is 66%? And I think, could I draw the AUC curve on this? So the AUC curve, oh wow, it is that. Is it? No, is it? Because 66%. Maybe, I think because you might go all the way over here, because we went through one of these right here. I think it is, because there's only 3 spots right there, and then there's only 3 spots right here. Yeah, okay. So, so if you look right here, let me draw this right here, and I think this might make more sense to people, because this is kind of helping me out to even draw it out and like think, why is it this? So you guys can be like, whoa, if we draw this out right here, because the more you practice drawing things. So these are the true positives, and these right here are the true negatives right here. So you've got here the true positives and the true negatives. So when you move through this, you have to go through one true negative right here like this, and then you go through all your true positives, and then you go across your true negatives. So if you look at the spots you'd go across, I'm going to kind of mark them as I do them. So, well, that's the starting point. So you'd go right here, and yep, so that's right there. Then you go right there, it's right there. Then you go right here, it's right here. You go right here, it's right here. Go right here, it's right here. There. And then if you look at this cube, since this is a 1x1 cube, so this is a 1x1 grid right here, what percent of the curve what percent of this grid have I shaded in? Connor or Joel, what percent of the grid have I shaded in right here? Since it's a 1x1, and that's all thirds right there, what percent? And so that should show how the AUC is being calculated underneath the curve. Yeah, we can do the hot dog. Is this helping out, making it make more sense right here? So if you look at how I kind of did that right there, that's computing it. Can you explain how it only got one thing wrong when there are 2 more nodes at the bottom? Correct. So Christian, great question right here. AUC is contained in I think AUC 0 through 1, it's contained in the vector 0 through 1. I think you're saying, yeah, AUC has to be between 0 and 1. I think that's what you're communicating. Connor, yes, exactly. And we'll do the hot dog problem next. It properly ranked them. So when we talk about what AUC means right here, AUC properly ranked them. So yes, the yes class received a higher probability than the no class 66% of the time. And so that's what's going on right here with the AUC. Does that make sense? The yes class received a higher probability than the no class 66% of the time. And then you can draw it out visually right there. I'm going to reach up and grab that. I can actually grab things up above my head now. I've got a much larger green screen. It's not as perfect as my last green screen. I'm too close to it, I think. But limited space. So, but yeah, do you guys like the new layout? Is it pretty easy to hear me? I didn't do any volume checks, but I was doing tests all yesterday. And thank you. I know people were asking if I could get online yesterday, but I literally totally redid everything yesterday. Hooked up everything, broke a cable. Yay, broke a cable. Apparently, I don't know how to unplug a DVI cable, or no, DisplayPort cable. So now I gotta wait to get a new DisplayPort cable. It sounds nice, that's awesome. So I've got sounds great, awesome. I've got a mic, a press, and yeah, I wish I had known that. I think I just broke the cable, but yeah, I didn't know it had the thing. I was like, this thing is really in there, and then it did a weird pull. I was like, what's going on? Yeah, didn't know that about DisplayPort. Found that out the hard way. I'll never forget breaking a DisplayPort cable, and I don't have a backup. And funny thing is, I have every other cord you could ever want. Not literally, but I've got a lot of cords. I've got drawers of cords. So 15, 20 years of doing electronics. So I think they wanted the hot dog question. Was that right? Caleb and others were asking for the hot dog. They just want to hear my New York accent say hot dog. So we can do that one right here. Does that help? Does that make more sense? A Santa. I've got 2 coming in from Amazon, so I should be good. Connor right there. Oh shoot, I should have asked you. Is it DisplayPort to HDMI? Is it or well, yeah. I think I need DisplayPort to HDMI converter. Awesome. Good to see you, Jeff. I was playing some Slay the Spire this weekend. I need to finish Ori and the Blind Forest. Connor, are you playing any video games? We'll do that, and so good to see you, Jeff. I'll be seeing you around, I'm sure. So my hair is getting so long. I'm just looking over my ears right there. So let's do the hot dog question right here. So with the hot dog question, we need to know our notation. So every time people see me do one of these problems, I go in here and I grab the notation. So we go here, we grab notation, and we put it in here. So exactly. Oh, is that the one you got right there, Connor? Maybe I don't know if I got that one or not. I'd have to take a look. I've got, I can't remember which one I got. I shouldn't have. I should have known something was weird. I thought it was like an HDMI. It's like every other cord, I thought. You know what I bet it is? I bet Jason unplugged it when we unplugged it last. I bet he was the smart one who didn't just rip it out. So that's what I get. Should be more careful. So I was like, I pulled wires out of computers, and I was like, this one's really in there. I'm an idiot. Okay, enough of Ryan being an idiot. So let's go right here. A nutrition laboratory tests 60 reduced hot dogs, and they found a mean of this. Now, here's the biggest thing. Whenever we see this, we need to mark the notation and do it accurately. So practice, practice, practice. Pause the video right now. Hopefully people do those things, and see if you can tell me what the notation on these things are. We're going to go for the easy one first. We've got right here that this is n. Then we go right here that the mean, this is going to be the mean of those 60 hot dogs. You have to be careful because there's a lot of different means. We've got y bar, we've got mu, and we've got mu naught. So mu naught, see you, Connor, thank you so much for stopping by. Y bar is a sample mean, so it must have a sample size. Mu is the population mean, which would be for all hot dogs. And then mu naught is a hypothesized mean right there. Just felt like brain or something. Adios. Hasta luego. Yeah. It's truly hasta luego. So I think that's see you tomorrow. So yes. And here we are is 37. So now we have a few standard deviations. We have S, which is sample standard deviation, which that one is. And then we have sigma. And then we don't use this in this class, but there is sigma naught. Anytime you see that naught right there, that means hypothesized, like you're hypothesizing a true proportion. And so we have S, which is sample standard deviation, sigma, which is population standard deviation, and sigma naught, which is hypothesized. And then, I might show something off after this. So there we go. We know what our notation is. Go close to the mic right here. We've got all of our notation written out. We're ready to go. Now, the biggest thing we need to know now is how to make the confidence interval, which is y bar plus or minus t n minus 1. There's a star here. You get to pick it. S over square root of n. Now, we're going to show off some of the power of coding real briefly right here because Connor, who was just here, showed us something really cool. We've got 60, 311, and 37. We go right here. We type in, what was it? 60 was the sample size, right? 60 is the sample size. 311, I think, is this. And let's go back. 311 is the sodium, and 37 is this. Does it want a 95%? If it wants a 95%, we go right here, and here's the confidence interval. Rachel, after this, can you do a question? Yeah, the birth twins, we'll do that one next. You got it, Rachel. So we go right here, and we can get our confidence interval. Now, you guys don't have this, but this is going to be a really good check for me. You can download R and get this. All the code you're seeing right here on the screen, if you do want to download R, it's not the craziest thing to download. It's kind of fun. But all this code you're seeing right here with the package, which is just something on the CRAN server, and then you bring up the library since you just downloaded it, and then you run this code right here, and it figures out the confidence interval for you. Here's the answer for the confidence interval, and you can also do tests right here by putting in a hypothesized mean. So this will give me a p-value of 1 and a t-score of 0 at the top, because I'm testing the value that we see in the sample mean. That'd be a t-test, which we're not doing right there, but this is kind of cool. I like it because I can check my answers when I work them right now. Nothing like checking your answers. Awesome stuff. So all we're going to do is we're going to plug in the numbers right here of 311 plus or minus, and now we have to go get this t. To get this t, let's go over here to our t-applet. These are 60 hot dogs, and I think we want a 95% confidence interval. 60 has 59 degrees of freedom. We make a 95% confidence interval. The t is 2.001. We're going to double check to make sure that's what it wanted. Was it a... So let's make it smaller. 95% confidence interval, 59 degrees of freedom. So make sure you check your percent confidence is 95. There's the percent confidence. Make sure you check that n minus 1. And then you go right here and you see 59 degrees of freedom and 95% confidence. So we are good on all this. We do have the right stuff. And we go back to our word sheet to where we're working the problem. So this is 2.001. Now notice you do not include this or this. The star means you get to pick it, and the n minus 1 is the degrees of freedom, which you use to find the right thing on the t-applet. So you have to go to the t-applet to get all that number right there. Now the S is going to be 37, and the N is going to be right here. Oops, it is right there, so let's put it there, and the N is 60. So that's the sample size. And finally, last but not least, let's go over here. Let's solve it. I do square root of 60 first, because that's going to go on the bottom. 37 divided by this, that's the standard error. The standard error is just this right here. And then we multiply it by 2.001, and now this is the margin of error. So the margin of error is going to be, the answer should be like 320.558. We're going to look at R, and we do get 320.558, and we get the minus. All you would do right now is just add and subtract these numbers. You'd go 311 plus this, and 311 minus this. So you can still do it without R. So if you notice, these answers I'm getting right here, I'm doing it all by hand. You just go 311 plus this, there's your first answer. 311 minus this, there's your second answer for the plus or minus on the interval. Once again, R is just letting me check this. If you do want to get R, it's fun to learn how to program. We got time now. So yeah, I love programming. Everyone knows that about me. And let's go here and let's put in these numbers. So we're going to go right here. We're going to check. Make sure, do not make an error. It's so easy. 320.6. Now it wants to 1 decimal, so make sure. And if you do get a decimal error, please tell me. I will correct those things. 301.4. I'm always afraid I'm going to make a mistake on these. And you guys tell me, like, Brian, wrong number. It happens all the time. So I think those are right. We would assume that these are going to be random. Let's see here, right? Normal. There we go. We need to do the random. Random's also independent, random/independent, less than 10% of all hot dogs, and they are normally distributed. So that should be good right there. I'm going to make it a little smaller. Is the randomization condition met? I hate this question. We don't know, but it's reasonable to think. I always get afraid when I answer that one, but I think I always get it right. Is the 10% condition satisfied? Yes, these hot dogs are less than 10% of all hot dogs. Is nearly normal condition satisfied? We can't see it. We can't see the distribution, so we can pretty much assume it's safe. I hate those. We will show you the distribution on our test or ask you theoretical things. Explain clearly what this interval means. I am 95% confident the true mean sodium content of these hot dogs is contained in the interval 301.4 to 320.6. I am blank percent confident that the true blank is contained in the interval blank to blank. I am 95% confident the true mean sodium content of these hot dogs is contained in the interval 301.4 to 320.6. And so we go down here, we find the one. We are 95% confident the interval contains the true mean sodium content of these hot dogs. We double check our answers because it's so easy to get one thing wrong. I think we've done it right. Let's check answers. And we got 100. There we go. Good stuff. And I think we're going to do the twin question next right here. Let's take a look at that twin question. So let's hop in here to the twin question. Okay. Great question, Rachel. And so good to have everyone here. I do want to point out, these are confidence intervals. When you look at these graphics, I would assume these are 95% confidence intervals, which means we might not, hopefully we're lower than all these numbers are projecting for all the fun stuff around these days. But we did have 2 good days in a row. Very good stuff right there. But these are confidence intervals right here. And it's a time series. So this would actually not pass our independent and random. You'd actually have to use time series on this because it's all like the next day is dependent on the previous day. There's a pattern to this. And so these are all confidence intervals. So when we were just making confidence intervals, the importance of confidence intervals, understanding what it means is kind of a lower and upper bound on what's going on. And there's a lot of uncertainty towards the middle of this month. So hopefully we go towards the lower end. I don't know so because I know how the models work. I know how the confidence intervals work. So there it is. Shaded index indicate uncertainty. Yeah, is it what? Look, oh, it's behind my head. 95% confidence intervals. Yep, sorry, the green screen's like having a harder time with black. But 95% confidence intervals right there. So when you think about the importance of what we learn in this class, we are doing the same sort of predictive modeling that you see right there. So that is huge, huge stuff that they're using predictive modeling. We're using predictive modeling. Very, very big stuff to make confidence intervals. And understanding, well, someone might say, well, wait a minute, we were actually lower than that. And it's like, well, that's a 95% confidence interval, which means we could go higher than that. So the 95% confidence interval, we would expect 95% of 95% confidence intervals to contain the truth 95% of the time. So all that good stuff right there. What we're doing in this class is very related to these predictive models that we're seeing making all these predictions. So I find it very important to understand like what it means. Like if we're outside that model, that can happen. You'd be outside the model 5% of the time. Yeah, sure, Caleb, we can do that next. Name a problem, Caleb, and we will do that next. Just be like, do this problem. Like the birth rate problem, the waiter problem, the carbon monoxide problem. If you just say do that problem, I will wait, that's good to have you here, Caleb. So, and Rachel. We are finding, here we go, the pregnancy birth rate problem right here. Okay. In 1990, a national vital statistics report indicated that 2.8% of all births produce twins. Is this rate of twin the same among young mothers? They have 111 twins from these young mothers out of 542. So we're going to have to take and put these numbers in, and let's do it. Oh, I got the thing right there. I'd like to, wait, 1 second. There we go. Nice and easy to read. I need to watch videos on how to light a green screen. I worked on it so much last night. It looked so bad at the start, and then I got it to where I liked it, and I was like, okay. And I swear, every time I boot it up, it changes. Like, I'm like, why does it look different? I just fixed the settings. The studio green screen was so much easier. Okay, so in 1990, Vital, there we go. Okay, so what do we do when we get these questions? We always mark our notation. So we're going to go here and mark the notation for this. We've got here this. We don't need 1990, and this. So I need your guys' help in the chat. Let's see if anyone can tell me any one of these numbers. You got to get me started here with any one of these numbers. There's an easy one to do. What are any one of these numbers that we have right here? I need to know any of these numbers. Pause the video. See if you can write your notation. It's great practice for the test. If you can identify the notation correctly, you can probably pick the right formula because you'll get a sheet of formulas for the test. So if you have the right formula, if you have the right notation, you'll probably get the right formula, and that's what you want. You want to get the right notation, pick the right formula, and solve the problem. What are any one of these for 1 million points in the chat? Does anyone know any one of these questions right here? Any one of these notations? So you understand the process of it? Cool. We can we can do that one next year. I can explain the very end of that. I might give away the answers. I don't know how many people we have watching. So if there's only like 2, both people might be like, I'm stuck. So if it was class time, I'd be like, nope, we're not moving on. But right now I'm going to tell some answers. So, yes, great job, Jessica, right there. Jessica, 1 million points, amazing work. And so if you guys didn't know this, and Caleb and other people check this out, I don't know how often you guys come to the chat, but you can do exclamation mark points, and you can look at the points you're getting in the chat, so you can see like how much you've been chatting, and the more you chat, the longer you stay, the more points you get. So it's kind of a fun thing that we have in this chat that you can look at your points. And Jessica, amazing work right there. Good practice. You got it right there. So I have 195 mu bucks. The more you stay, the more you chat, the more points you get. So something I'm working on, probably how I'll do extra credit in the future. So that way it's really easy to track, really easy to know how much everyone has. And you just come into chat and talk. And so, yeah, good to see everyone. So now we need to take X and N and get P hat right here. I don't think we're using that one for that one. Don't scale the data frame because I think you're taking the log of it, Evan. So if I'm thinking of the correct problem, you want to go in there and add a certain value to it. Is that correct, Evan? So you need to find out the minimum of it. So try running the min of it, and then you need to do the min. Like one of them has a min of like 773. So if the min is 773, you need to add 774 to that. So you could take the min. Take the absolute value of the min plus 1, like think negative 773, absolute value of that 773, plus 1, 774, and then store that as like min plus 1 or something like that. Store that in, and then add that to every value in the data frame. Does that make sense right there, Evan? Does that help out with that? So you want to find the minimum value. You want to take the absolute value of it. You want to add 1 to it. But then you also want to look at it to see if it's I can look at that here in a moment here, Evan. And I'll do like one of those here if you want. But yeah, just tell me where you're stuck. Great questions. So with X over N right here, we've got P hat, and P hat is the sample proportion. You're welcome, Evan. Stay around and we'll do that right here. So this is going to be P hat. I got to remember my head's blocking these things. So P hat that's P hat, the sample proportion. So I think we can get this right in here. I'm in different spots. Like I used to be just a tiny little window, but do you guys like this better? I hope. I spent a lot of the weekend. Yesterday someone emailed and I was like, they were like, can you do this or that? And I was like, I'm setting up a whole studio today. Between answering emails, I reformatted everything. So that's why we're able to actually get a further out shot right now. And I'm able to reach the sky. I'm able to, like, it's really bright, I know, and so I just don't have room to set up lights probably properly. So, but I'm liking it a lot better. I can kind of be like, look at that right there. That's P hat right there. I know you don't look, you can see like the screen going a little crazy right there. Okay. So what do we got going on? We need the formula now. The formula is going to be P naught minus P hat over P naught Q naught over N square root. This is going to equal to a Z-score. Now, I should slow this down right here because we really need to do this in the steps. So let me make this question a little bit slower, because the first step for any hypothesis test is going to be write out the null and alternative. So when we write out the null and alternative, it helps to know the notation. So, awesome. Oh, that's awesome. Glad to hear that. Thank you, Jessica, very much. No, I'm glad. I want students to know that I'm there for everybody. Like, we got this. We're gonna get all through all this, and you guys are doing excellent. So P equals P naught, and P naught equals P naught right here. So thank you, Jessica. So much positivity. So that's so awesome. All we're going to do for this is put in P naught and 0.28, 0.028. Boom, we got it right there. We've got the null and alternative written. Now we're going to scroll down just a little bit, and we are going to go here and do part number 2. That's this right here. So we've already kind of got that written out as part number 2. And so we're going to put in P naught and 0.028 minus, oh my gosh. See, Jessica, this is when I make the mistakes. P hat minus P naught. I knew something looked weird there. It has to be the observed minus expected. It's always observed minus expected. So you always take what you see in a sample minus what you predict it to be. So we observe a P hat, we expect P naught, which is what we hypothesize to be true. So some statistician out there saw that. I hope they watched the rest of the video and know I corrected myself. But we get right here. And what you'll notice is we observe something lower. So, oh, yeah, well, whichever part you're stuck on, feel free to ask, and we will work on that. It's so long right here. That's a lot. And then we have to put the P naught down here. Ask any question you have related to any problem, and we will... Is it this part right here, Rachel, where you're trying to do this? And this will equal the Z-score. So we have to be very careful right here that we have a Z-score. And I might see if I have this in the other program. But have you followed every step right here? Can you read my handwriting? Please note that I'm just solving this formula right here. This is why notation is key, is that we have P naught, Q naught, and we have P hat minus P naught. Notation is so key. So do you have any questions right now? Like, how'd you get these numbers? Are you following along with these steps right here? It's, we identified P naught, and I'll scroll up just a little bit. So you can see where we have P naught up there highlighted, where we have X highlighted, X over N is P hat. So we need to take the P naught and put P naught right here, not like that. P naught, Q naught, N, P hat, all this stuff right here. So very, very important just to get each thing correctly in there. Are you on every step that we've done so far? If you're not, feel free to say so and we will fix it. So now we will, I think you're good. Tell me if there's any issues. So how did you get HA? Like, how did you get not, oh yeah, great question. Jessica, amazing question. It asks, and I should have highlighted this. Sorry, just a little bit congested. I'm totally fine. Just that's congestion. That's not lower respiratory. So is the twin rates the same among young mothers? So the twin rate would either be the same or the twin rate would be different. Awesome, Caleb. Glad to hear that. Yep, it's good practice. Listening in. Caleb, excellent work. So the alternative here is that the twin rate would be different. So it's either equal to the twin rate or it's different than it. So when they ask, is it the same? the alternative would be if it's different. So the twin rate is either the same or it is different. Does that make sense right there? The twin rate is either the same or the twin rate is different. We've only got one of two options. The twin rate is the same, is the null. So this would read the true, awesome, great work, Jessica. The true proportion of twin rates for these mothers is equal to this. The true proportion of twin rates for these mothers is not equal to this. So it would be different. Great question right there. Sorry, I should have explained that, but I really appreciate you guys asking that because I bet you someone else was wondering that too. So we now solve through this. And what do we get right here? We go in and we get, there is that. That is the, well, we got to do the bottom part first. So we go this right here, P naught times Q naught over this right here, square root, that's the bottom of the equation, 0.0209 minus 0.028. We should get a negative number. We do, divide by this. Oh, good, that's awesome. Since I got this z-score, I probably know what the p-value is going to be. So we're going to guess the p-value. That's one of our favorite games, guess that p-value. We're going to hop back over to the question. Are the assumptions met? Yes. We're going to assume these are random mothers. I think it says random right here. There we go. They were... I'm going to assume it's random. I wish it said it, but I'm going to assume those are random mothers. I've done this enough. We have here the alternative of does not equals 2, so we're good there. Here is the z statistic. And once again, we're going to guess this p-value. Now, look at what this rounds to. So I wonder how many decimals it wants on the p-value. It wants 3 decimals, which we might get it wrong guessing this, but since we are doing the two-tailed test, I want us to take a look at this. Since we are doing a two-tailed test, and we got a z-score of -1, then what would the p-value be on the two-tailed test? This is a decent test question, and we might make it multiple choice or something. So think right here. What would the p-value be? Does anyone have a very close guess to what the p-value would be? Does anyone have a very close guess of what the p-value would be? I can give a hint. Careful. Remember the empirical rule. Good guess right there. Good guess, but you're thinking of 2. If it was 2, it would be that. Because if it was 2, then the area outside of it would be basically that. So good guess. That's not really symmetric, but we'll pretend it is for the moment. But since it's only 1, outside of -1 and 1 is how much percent of area? The total outside of -1 and +1 would be... Sorry, my numbers are kind of colliding right there. The total outside, what would it be? The total outside would be very, very close to 32. Now, it's not going to be exactly 32. We use the empirical rule to estimate. I believe it's something, I think, wait, what am I doing? So 0.68, I think it's 26. So if I do 1 minus this, there we go. So I think this would be, so if my z was, how do you calculate the p-value? Yep, we'll use an applet. So let's show how to do that in the applet right here. Sorry, trying not to be congested. Let's go over to the applet. So let me bring the applet up. Here is the applet. Rachel in the chat, I think Rachel was asking that. So the applet is 2 seconds. So if you get the z-score right there, I'll show yours, Rachel. You ready? So with your z-score, as long as you did the z-score correctly, let's hope, you'd go here and you'd do outside, and I would carry all your decimals as much as you can. You're probably good on it though. And you do this right here. And there is your p-value. Now remember, mine was this right here, and using my knowledge of the curve, I estimated it to be this. So I was pretty close in my estimate with what I know for the decimals on it. So I probably would have gotten it correct. And I wonder if 32 would have done it. Does this make sense, Rachel, on how to use this applet to get the area outside of it? This is my value right now. My p-value will be this, and I estimated it to be this with my knowledge of how the empirical rule works. Basically 32%, because 68% would be inside of this, and we're doing the outside of it. Does that, okay, good, awesome, glad to hear that. Great job, Rachel. So, and feel free to come to all these office hours. We work through every problem we can, helping out learning how to do this. We're going to see if we would have gotten it right with 32 because it's kind of cool. When we can guess things. So if we get that one wrong, don't worry, that's on purpose for whoever's watching this video. So let's hope we get the 100. Let's see if it's nice enough on that plus or minus error. So what is your conclusion? This is a super high p-value. Watch out because it can be low or high. So since this is way higher than 0.05, we're going to fail to reject. That's the only option. And we got two things wrong. What is going on right here? This is going to be this one right here, which did I get the p-value? Did I get the z-score wrong? Okay. There's an error in my mathematics. That's what that means. This is what happens when Brian's under hot lights for a long time. We did an error in the mathematics. Okay. So let me check my numbers. That's that. So 0.28. Let me check this. That's that. Divided by 542. That's that. That's that. Cool. It wants to know if it's different. My brain has broken today. So, was there a separate video where you went over the chapter 14? I think I did. I think I did it in the most recent video, or I think I did it in the really 4.5 hour long video. And this problem right here, let's see where I went wrong. What did I do wrong? So are all the conditions met? Yes. Support the null alternative. It's got to be these right here. We're just going to check to see if it is this, because that should still get it wrong. That still gets it wrong. Round to 2 decimals. I have seen these things make errors before where it won't accept any answer. So select the right p-value. So right now so I'm going to solve this with actually R. Did I type in the 11 divided by 542? There's that. 0.028. Did I type that in right? Let's do it in R. So there should be one prop inside of R. Oh, it does it differently. Well, let's solve it here. X equals 11. N equals 542. I have seen my Pearson mess up before, and I'm hoping this is one of those weird instances. There's P naught. Let me make sure I get all my numbers right. So there's that. Let's store Q naught in here. And then Q naught is going to be 1 minus P naught. So we got Q naught, we got P naught. And then let's go here and do standard error P. And that is going to equal, so that's P naught times Q naught over N. And then we square root this whole thing. So SQRT. And that was my, let's see that. That was that. Sorry, everyone. And then we go, we need P hat right now. So P hat is equal to X over N. There's P hat. And then we go to Z. Z equals P hat minus P naught over standard error of P. And then we go right here and we do this. And we get, do we get the -1? Wow, what am I doing mathematically wrong? How am I making them? Well, now this is correct. So we do have the right answer right here. So now we're going to guess it. So this is the right answer. Can I just not read the calculator? Was that it? Was that an 8 and I saw the 0? Oh, let's see. It looks, that's quite different. So I wonder where I made my math error. I'll have to review the tape and see that. Everything should be correct now. I just can't do math today. The problem is usually algebra. So this right here is going to make it's going to go to 9 right there. That's going to make the p-value smaller. So now we're going to guess the p-value. 1.2818 is 10%. So this one drops off pretty quickly. This is a very hard one to guess. It's probably going to be about that. I probably didn't see, now we didn't get that right, but that's all right. I was guessing that one. Let's see how close I was. So here we go. Let's go back, and I want to find out where I made this math error. So we're going to go outside of this. It should like this. 27, I guessed way too quickly. So, because that's 20%, yeah. So the answer is 0.276. And let's see where we made the math error. So let's check answer. Now we got 100. Good. So the math error was right here. The z-score was wrong. Somehow we made a math error. Let's find out where the math error was. Let's check all of our work by using R, and it will carry all of our decimals. We're going to call this up here the difference. So what was going on right here? Here is p hat. Let's look at R. And we have p hat calculated right here. So let's do p hat. And that's the same p hat I have. So when we took the difference on the bottom, oh, you know what I bet I did wrong? I bet my Q naught is wrong. No, Q naught on the bottom of my equation, P naught times Q naught over N square root, and then P hat minus P naught. Did I just keep, I can't believe I would make the same error multiple times. Let me try punching this into the calculator again. I mean, obviously I've done it right over there. So there's P hat minus, well, we do the bottom part first, 0.028 times 0.972. Did something like that happen? 0.028 times 0.972 divided by 542 square root. And we've seen this standard error multiple times. Let's check our standard errors. So the standard error right here, since we did get it correct, this is correct. And now let's look at this answer. Same exact answer. So yes, everything's correct right now. We're good. And then all we do is we take the difference and divide it by it. So what's going on right here? Am I somehow, where am I doing the wrong division at? Not the long division, but the wrong division. So I've got this copied in right here. 0.02029. Oh, is it the more decimals? You know what I think it is? Wow. I think I know what it is. Oh, now we get the right answer. Hopefully chat will tell me what I did wrong, but if please note, I have not changed what's written on the screen right here. So I'm doing 0.0209 minus 0.028, and then I get this right here. I divide by, and I get, okay, wait, this is some magic right here. It just showed the right answer, I swear. 0.02029 minus 0.029. Oh my gosh, is that what I'm doing? Do not sit under. Oh my god, I bet I'm punching 9s or 8s. It's math errors will do you in. A math error will just wreck a whole problem. So very sorry. I know. Don't worry. I feel it. I make them too. And it's just you type one wrong thing. That's why I really love doing it in software, because I can look at what I write and I can check it out and I can make sure I'm doing it exactly what I want. And then once I store what X is, what I store what N is, then if X and N are right, that's P hat. I can store what P naught is. I can get Q naught and make sure it's perfect. I can get the standard error. I can get the Z-score. And even here, I can get the P value. If I go and do 2 times, we want to go to P norm and P norm Z. I think that'll do it. And there is my p-value, 0.276. So good, awesome. So thank you so much. This was my redemption right here by doing it inside of R. So if you notice right here, there's the p-value, and then here's the p-value here. And there's probably a plus or minus on this. Probably if we put this up here, it'll still like it. Yeah, it still likes it. So just because R is doing it more exactly by all the calculations, it's carrying more decimal place accuracy. So we are able to get it, and that's still accurate. And this is all of it done inside of R, but I'm not doing inside of R all the time because you guys don't use R. But this is the way I would do it when I'm solving it. If I'm going to write it out, I would do it inside of R, because then I can just track everything I have and get my p-values. The reason I'm doing 2 times is because this does 2 times the lower p-value, and instead of getting just the lower tail, I can get the upper tail too. So if I did 1, it would only give me this area right here. And I think did Caleb have a question? We would not reject the null here. We would fail to reject it. And of course, this p-value now. Caleb, which one do you want me to do? Which question do you want me to do? I'll turn my brain back on. That's a 9 right there. So it's a little further out. It's a little smaller than 32%. So if you can see, since it's that's why it's like 27%. So Caleb, any question you want, feel free to ask. Be like, hey, Brian, do this question. Like whatever question you want. Math errors. Part C on the bank one. Let's do the bank one. Okay. Part C on the bank one. This is a bank is going to give out loans. And let's do it. Don't make math errors, everybody. They're too easy to make. And then you lose points. We don't like that. So I think I got the wrong window. Is it in this window? That's the, yay, fun stuff. Go back here. And, okay, I think Oh, okay. Give me 2 seconds here, Caleb. I have to pull it up. I think I might have closed out of my Pearson. So I will pull up my Pearson right here. And let's do the bank problem. Okay, the bank problem. As the homeworks get closer to being due, I'm sure we're going to have a lot more people. And thank you, everyone, for being here. So we go to Assignment Manager. And we go down to Chapter 14, Sampling Distribution for Sample Mean. We go to Replace Questions. We click here. And then we bring it over to here. Okay, let's see if we get the bank problem. This is the... Here we go, pregnancies, CO2. Here we go, this. Was it only? It's only on the homework, it looks like. So let's go back and grab the homework. And chapter 14, homework, sampling distribution for sample mean. And let's go to replace questions. Let's go here. And here we... Oh, there it is. Go. Okay, what's up, Caleb? Let's solve this question right here. It's one of my favorite questions to solve. This chapter right here is one of the ones that when you get down, it's it's really just a pattern. Let's grab, once again, always we start our problem by doing this. Here's your best practice, is to take this and know your notation from the problem, because when you get a question on the test, it's not gonna be like saying this is the notation or this is the chapter you're doing. So, and I think you've got it right there. No, yep, you are correct. Caleb, we're just gonna do, Caleb, you already got the answers. Caleb, 1,000,000 points. Don't know if you're in our section, but if you are, you got the 1,000,000 points right there. So we know that mu p hat equals p. So we know what p is equal to. So we're gonna solve that right there. And now we're gonna go right here. We're gonna pull up a new sheet real quick, and we're gonna write, we're gonna drop our pen. We're in a new worksheet again. So we're going to go right here and do, we're going to look into the problem. We're going to mark our notation on it, as we always do. We've got this, we've got this. So this right here is P, and this right here is N. And so what do we got going on? We're going to find out that Q is equal to 0.89. Nice job, Caleb, right there. And then we are going to remember that mu, let's write a better mu than that. Mu P hat is equal to P, and SD P hat is equal to P times Q over N square root. My class knows that quite well. So we're going to go right here, and we're going to delete where these things are at and replace them with their values up above. This is why knowing notation is key. So we go right here, we put this in. We're going to write really small right here. And can you do the Golf Country Club one? Yep. Or the medical research? Yep. We'll do that here next. You got it. So there we go. We've got all the stuff inside of here. We're going to solve for the standard deviation of the sampling distribution. So 0.11 times 0.89 divided by 300. And we get this right here. We got to square root it. Hopefully no more math errors. And this is the standard deviation. Now, once you solve these in this problem, this is the hill that you just have to get over. Because now we're just going to delete it down to 3 decimals. It's going to like it. Good. And then we're going to do the last part, or all conditions yet. Less than 10%, or randomly select people to give loans to less than 10% of all loans, and then we have at least 10 successes and at least 10 failures. We would expect 33 successes and 267 failures. I did that by multiplying 11 by 300. I can show it right here, that we would take and we would say 0.11 times 300, and we get this right here, and 0.89 times 300 is 267. So we'd expect 33 successes, as in 33 people to default on their loans, and 267 people to not default on their loans. So that's got that right there. Make sure you don't click in the wrong spot. You can lose points by that. I've done it, maybe today. And then we continue on to the last part right here. Now it wants the probability of over 12%. This is where we like to take our guess. So that's about half a standard deviation. That is a very hard one to guess. Super duper duper hard. So I'm not even going to check it, because this is only about half a standard deviation higher. So it's going to be about 28.2%. Now, if I got this, I'd be super happy. I don't want people seeing that I get it wrong. That's not how you solve it. You go over here to this applet and you put in your numbers. Now, I like to do it the way my Pearson shows it. and we're going to put the numbers in right here and go above 12%. So what we're going to see is 12% is right about here, and that's a little bit more than 25%. So 28.9. And so that's rounded to 28.9. Here was my guess. That's probably not close enough for my Pearson. Nope. 28.9 is what it wants, and now it's got it. So once again, I just wanted people to see that we did get it correct, but my guess was super close to it. I was guessing based on what I knew that it was about 28%, and I was right. It's 28.9. I said 28.2, but that's a very hard one to guess because it's towards the center of the curve. It's just if something out here, like I know that's 2.0023, I think. So if I punch that in, that'll be 0.0023. 0.0228. Sorry, I might have said a second O in there, but it's a little bit less than 2.5%, because 2.5% would be 1.96 standard deviations. This right here would be very, very small. How did you get the 12? Ah, yes. Great question, Caleb, right there. We did 12% because the question said over 12%. So we went to our curve and we said, what's the probability that over 12% of people will not make timely loans? And this is where I got 12 from the question saying, what's the probability that more than 12%? So I went greater than 12 because of the over, and then 12 is what I selected on the curve because more than 12%. The way this problem works theoretically is you're looking at banks giving out a loan. They expect 11% of people to default on a loan. But if you give a loan to 300 people, what would happen? If you give a loan to 300 people, well, you would expect 11% to default, but 12% of people would default, like 12% of the 300 would default about 28.9% of the time. So it could happen that more than 12% default. Sorry, I should have said more than. So you would expect 11% to default. What's the probability that more than 11% of people default on their loans? Caleb, do you know that one? What's the probability that more than 11% of people would default on their loans? Using this curve right here, what's the probability that more than 11% of people would default on their loans? Million points. Anyone in the chat? Big points right here. And then we'll do Rachel's questions next. Rachel, do you want us to do? We'll do them both. So pulse rates and country club. The answer would be 50% because that's at the middle of the curve. So above that would be, so, well then below that, if you want to do below 12%, like if we did below, you're right, this would be above 12%. If we did below 12%, I might have said 12. Sorry if I messed up. I might have said 12, Caleb. Below 12% would be minus that. Above 11% would just be above the middle of the curve. Yeah, let's do both right here. Does that make a little more sense, Caleb, on how these are coming from? It's just shading the percent of time we would expect this to occur. So all that good stuff right there. You're welcome, Caleb. Excellent work. So let's do, did I already close the web page? My Pearson page? Let's do this right here. More questions. So chapter 14 and confidence intervals for the sample mean. And let's do, okay, replace questions. And right here. Okay, medical researcher, we got the first one right here. Cool, okay. Oh, it's a theory one? I love this one. Cool. I like theory questions. They're a lot of fun because we basically just have to make sure we understand the theory, which is very important for the test. A medical researcher measured the pulse rates of a sample of randomly selected adults and found that the following, sorry, phlegm in my throat, totally fine, not lungs. Student T based confidence interval with a 95% confidence. This is the lower bound and the upper bound. So here's what you want to do. You want to do this. Every time you see a confidence interval, don't read my Pearson's answers. Don't be tricked by them. You want to do this. I am blank percent confident that the true is contained in the interval blank to blank. Okay. Don't read their answers. Don't read, you're welcome, Rachel. Don't read their answers. You want to say, I am blank percent confident that the true blank is contained in the interval blank to blank. So let's go check that out. I am 95% confident that the true mean pulse rate of adults is it. I'm 95% confident that the true mean pulse rate of adults is contained in the interval blank to blank. So the only one that looks like that is we are 95% confident the interval blank to blank contains the true mean heart rate. I wish it said of adults. This is not, it's that I am, so this is good. What is the margin of error? Now this is a huge thing for the test. Calculating the margin of error is nice and easy. People might be like, how do you say that? Why would you say that, Brian? I want everyone to figure this out. We're going to go to McDonald's, and a meal at McDonald's right now costs between $4 to $8. I want everyone, no, let's use $5 to $9. I'll explain why. I don't like the numbers repeating. If anyone wonders why I changed it. Easy to, Rachel, I bet you, I'll ask you questions. You'll know the margin of error like that instantaneously. Rachel, here, I'm going to solve this one for you, and I want you to see how I solve it. You ready? The meal at McDonald's costs between $5 to $9. So do you see the 5 to 9? So now I'm going to figure out the margin of error of this interval. The margin of error of this interval is half the length of it. Take that note that the margin of error is half the length of the interval. That's all the margin of error is, half the length of the interval. So what is the length of this interval? I'm going to take the higher part of it minus the lower part of it and divide by 2. And Caleb knows what's going on. So we're just going to do the upper minus the lower divided by 2, and it is 2. So and think about this. How could I write this interval? 7 plus or minus 2. So now I'm going to do one in my head a little bit quickly right here. Now we're going to go out for a steak dinner, and the steak dinner is going to be really awesome. So Caleb, everyone, we're taking the whole class out for a steak dinner right here. So we're going to invite Chelsea and everything, my fiance. So we're going to take everyone out for a steak dinner, and then it's going to be $30 to $40 a person. So what is the margin of error of this interval? What is the margin of error? Yes, Caleb, you got it. So all we do is we take half the length of it. The length of this interval could be found by Julio. Nice job right there. Good to see you, Julio. Rachel, is it making more sense right now? So 35 plus or minus 5. Caleb, amazing work. And once we know the margin of error like this, that it's half the length of the interval, and you can use it to find the upper and the lower, it makes a lot more sense. See, Rachel? Look at that. 1 minute, and you're like, that makes a lot more sense. That is easier. That's what I like to see. So how are we going to find the margin of error for this question? To find the margin of error of this interval, all we need to do is take the big number minus the small number and divide by 2. So we're going to destroy our calculator. That's what we're going to do. So big number, I know Pearson does make it seem harder. All we do is just take big number minus small number divided by 2. They're going crazy on these decimals. I'm going to totally type in a wrong decimal and get it wrong. 6. Oh, I totally did. So 67. I'm under hot light, right? And literally, if you look over here, like, there's bright lights shining on me, bringing out everything. So, like, it's very hot right now. So I run the air conditioner, and then I stream. So I don't, because bright lights are not good for small room. Big number minus small number. This is just the max minus min that people saw me do a second ago. Cool. That's right. Half the length. Okay, cool. So that is half the length of the interval right here, and it kind of makes sense. That look at it, it's 63 to 67. That kind of makes sense. Round to 1 decimal. Oof, that's so close. Everything right here, you have to be careful. Rounding to 1 decimal, this would round down. So we're gonna found the answer to this test. I just need to get on response like, yes, awesome. I guess it doesn't want you to copy them. That's cool that it does it that way. If they had created a 95. Now, here's the thing I want people to remember. Oh, Julio, I showed you this earlier, I think, but 68, 95, 99.7. I can actually reach really far out, even though my hand gets totally obliterated by the light. But I can reach really high today. I can reach really out. I've got tons of room inside this box, which maybe I might be able to make it green screen better if I don't have room, but I kind of like having the room. Mine is, yes, that looks right. Freedom. I'm free unless I reach way too far over here. Then I'll start to like disappear this way. But the way I can reach up is I can reach like way off the top of the screen. It's pretty cool. Just got a big green screen behind me right now. It's literally, this is why all yesterday I was like reformulating this room. So it's, it has to be one of the most crowded rooms I've ever seen. If I walked into someone's place and I saw this room, I'd be like, it's a lot of stuff. Okay. So if we went from a 68 to a 95, it'd get bigger. If we went from a 95 to a 99, it'd get bigger. 68, 95, 99.7. So we get this right here. The margin of error would be larger. The margin of error would have been larger. So we check all our answers. We get 100 because, of course, we do. So good stuff right there. And what was the other one we were going to do? There was one more, the country club one, I think you said. We got flight attendants ones. And great job, Rachel and everyone. Lowering more customers. Will your flight leave on time? T-tables. Oh, these are so fun. I like guessing these. Okay. Oh, that's a tough one. This one I'm not going to be able to get right. We're going to guess these. The golf country club one, we'll do that next. I'm going to guess these right here. This one, since the degrees of freedom are so low, it's a very hard guess. There's no way I'm getting this one right. If I get that one right, it's going to be higher. If I get that one right, that's amazing. That's a very hard one to guess. This one is not impossible to guess because I know some numbers. Sure, let's try that. Yeah, this one right here, I'm not going to guess. What if I got this one right? That'd be amazing. Like if it was the other one I got wrong. Yeah, that top one's so hard to guess. But we can get it right. 15 and 99. We go over here to our T-applet. We put in 15 degrees of freedom. We put in 99, and it's 2.947, so 2.95. It's just that's a very hard one to guess. So 2.95, and that should do it. That should get the problem right. And those are just using the T-applets. If anyone has questions of those, feel free to ask. Here's another T-applet one. This is impossible to guess. Now, not impossible, but it's going to be ridiculous. That's seriously like 15.23 or 14.25. I did one similar to it a few days ago, so I feel like I might be able to guess it. Now, I want everyone to notice, last time I guessed 2.38. When the degrees of freedom go higher, it goes more towards the normal. I know that this is basically 1.96, so I'm going to guess 1.97. Because with such high degrees of freedom, it's basically the normal. I probably got the second one right. I did. To get the first one right, I have to go to the T-applet. I have to go to 99, I think, with 104 degrees, or with 2 degrees of freedom. 9.92. 9.93 is going to round to. 9.93. So as long as I punched everything correctly, the right way, now we check, and we got 100. So you can kind of guess these. If you know the z-scores, how these work, and you understand how the t's and the z's work, you can guess those. So I always like guessing those for fun. Like it's like fun to see how close you can get. It's just if the degrees of freedom are so low, then the t is drastically different from the z. So the lower the t degrees of freedom, the more there's a z. So you can see this curve right here doesn't look like normal, but I can tell you what the answer will be. If I hit 0 a bunch of times, the answer will go to 2.57, and I think this only, 2.576. Ready to see 2.576? Here it goes. There it is. So since I know this will go towards the z, I know what it will approach with enough degrees of freedom. So I can make educated guesses at these because I know the z-score for most percent confidence intervals. So I know the z-score for the previous one was 1.96. So then I was able to guess, well, it's going to be a little further out because the t is smashed down. So I was like, well, there's a lot of degrees of freedom. It's only going to be a little bit further out, 1.97. So I think it was something like this right here. And it had like 104 degrees of freedom, and I might have guessed 1.97, but it gave it to me with the plus or minus on the question. So that's why I like guessing those, just to see how close I can get. Country club question coming up. Here we go. How far do the golfers at a certain country club drive the ball? Now, here's the really awesome thing about using R. Well, let's do it the right way, the way we should do it for this class to practice. So let's get our practice in right here. We really only need this grid, so we're just going to take the grid for the question. So let's take the grid, and let's bring the grid over to not here, not you, PowerPoint. So how do I access that table? Great question. You know how you access it? Watch this. We got magic right here in the chat. We're going to grab this. We're going to go right here, and I can actually copy this and send it to you. Nathaniel Johnson did a great job with this. There it is right there, Marissa, in the chat. So you can now access the table. You can now use this table right here. So all that good stuff right there. Oh, well, I lost the table now. The only thing we're missing in this is the degrees of freedom. I would probably go ahead and start marking your notation on this. That the count is n. You're welcome, Marissa. Ask any questions. Good to have you here. So we've got the mean is y bar. That's a sample mean. It's technically y bar bar, which they'll point out later. And then we have the standard deviation. It's working again, I think. How's it looking? Yeah, look at this. We got speedrun right here. Speedrun looks really good. So speedrun's looking great. I worked on how all the backgrounds look. So that way, it's just so bright over there. But we got speedrun, and I've even got the timer working even better right now. We'll see if the timer appears on the right screen. But, we should speedrun this question. Let's do a quick speedrun of this question. You ready? So we're going to start from scratch. You ready? We're going to see how long it takes us. This is our fun right here. So we got to speedrun this question. The timer's getting pulled up here. Okay, so let me put the timer on the screen it belongs on, because I figured out I could do this. And put the timer all the way over to here. Okay. Timer, you doing all right? Timer? What happened to you, timer? Let me bring the timer back to the screen. Okay. bring a timer over here. Cool. Let me see if the timer's working properly. Of course, timer's working. Okay, cool. Timer's working properly. Let's do a speed run of this question right here. We got everything going on. I thought I saw it. Did I see some slowdown? Hopefully not. Okay. So this is the golf question. We're going to do a speed run of this question here and see how we do. But you know what? Oh, I don't have the transition screen set up properly. Well, whatever. We're going to do a speed run of this. This is the golfer question, a speed run of it. Let's do it. Okay. So for with this question right here, we need to first identify our notation. Always identify your notation. So we see right here we have the count, we have the mean, and then we have the standard deviation. From this, we can get the degrees of freedom. The degrees of freedom equals n minus 1. And here I'm going to cheat. I'm going to do something I shouldn't do. This is our super speed run of it. We're going to take all these answers right here and put them into R. So we go right here and we use this right here. We've already got some code pre-written out, so we won't use the pre-written out code. We're going to go to tsum, and then we need the mean that it gave us. So the mean was 285.3, comma, and then we need the standard deviation. Standard deviation is 9.3. It's going to do the degrees of freedom for us. We need the count of 2.2. We run this right here. We go and we look at our interval. So let's go back and go to the question. And so the lower is 284. That's going to round 284. We go here, and the upper is 286.6. 286.6. Interpret this interval. What is the problem with this experiment? Okay. It's not skewed. The sample is not random because it's only the top golfers, and the data are for the mean. Is this a concern interpreting the interval? Yes, it is a concern because we're doing the mean of the mean. Check our answers. We got 100, and we did this in just over a minute. Man, I wish we could have done it in under a minute. That would have been so cool. And you can't see my answers really well in here. Maybe we'll hop out of the speed run and go to yeah, let's do it outside of R. Don't worry, I was doing that for fun here, Rachel. Here we'll get serious. You ready? We're hopping back to the desktop right here. Good afternoon, Charlie. So good to see you. We were having a little bit of fun there. Let's look at how to do it outside of R. Okay, so all R is doing is solving one equation for us. Remember, we first went through and got all of our notation. So we go right here and we do y bar plus or minus t star. Now we're gonna have to find this. N minus 1 degrees of freedom, s over square root of n. That was our kind of fun here. We've been going for a while under the light, so I was like, let's do a quick speed run of this. So we've got everything identified in this problem so far, except for the t star with n minus 1 degrees of freedom. We do know that the degrees of freedom are going to be 201, and these are a lot of degrees of freedom. Now, when we build a 95% confidence interval, the z-score is usually 1.96. But we don't want to do the z distribution. Let's go right here. We want to do the t distribution. So we want to go here to stat distributions t, and we're going to punch in the 201 degrees of freedom, and there's the t-score. If it makes it a little easier to see, we could do it this way, where we're shading the middle 95%. So this is the t-score right here we're going to use of 1.972. Does that make sense, Rachel, on why I identify the degrees of freedom, then I bring that over to the applet, and I put in the proper degrees of freedom and the proper shading and everything? I'll put it linked in the chat right here, but do you understand where I got the t? This is where usually students get stuck, is finding the t we need to make this interval. To get a t for the interval, you need the degrees of freedom and the percent confidence. Shade the percent confidence in the middle, and then choose the right degrees of freedom, or choose the right degrees of freedom first, I think. But that link will bring you right to the graphic I just made right now. Does that make sense right there, Rachel, on how we got this? Good, awesome. I'm slowing it down right now. Right now it's not a speed run. We just got the world record for the speed run, but we're just doing normal solving right now. So now we go here and we put in 285.3 plus or minus 1.972, and then we go here to 9.3, and we go divide by. Computer's fan actually turned on. That's interesting. Rarely hear that. And s over square root of n, so 202. So we've got all of this right here ready to solve. So Amazon shipment. Oh, good. Package shipped. And so let's go right here and do 202 square root, and then let's take 9.3, divide by this. That is the standard error. So all I solved was this right here, which is the standard error. This is the standard error. Then I'm going to times this by 1.972, and then we get this right here, which is the margin of error. And then I go and do 285.3 plus that, and there's the answer of that, and 285.3 minus this, and I get this right here. Does that make more sense, Rachel, on where these numbers are coming from, how to solve it all, and get the exact answers? Does that all make sense right there, Rachel? How are we doing on those questions? So hopefully that all makes sense. The last little bit about this question, I think the waiter waitress problem was next. The waiter, Caleb, we'll do that one. You got it. Let's do that. So this last one right here, we didn't choose. How can you solve? Yeah. So we didn't choose random golfers. We only chose the top golfers. So that's an issue. If we want to talk about all golfers, we can't interpret this interval for all golfers. It's for top golfers. And then also we took the mean of their times. This is when you do confidence intervals, you're supposed to take individual points. You're supposed to do it for the individual points, not for the mean of all. So this is a problem right here with this. We're not doing a confidence interval properly. So that is a problem. This is not a properly constructed confidence interval right here. So we do have some issues with this. I wish I could I need Jason. He would tell me why my green screen is not perfect. He set up the green screen perfect. That green screen we have in the studio, man, so perfect. I wish. When I get to the new place in Texas, I might just literally paint a whole wall green. I'll still use this green screen since we got it, or I got it. But sorry on that. And I'm lucky green screens are out of stock. I wonder if green paint's out of stock. So yeah, I might just paint a whole wall green. That'd be fun. Just like go in, paint a wall green, and then I'd have all space. I could literally frame my whole shot up and like run across. I could be like, let's go look at this over here, and like go to anything I wanted. So and then just get it properly lit without some hot spots. So it'd be amazing. No shadows, no hot spots. So waiter waitress problem. Does this make sense on the multiple choice, Rachel? Is that we should do confidence intervals for the mean from individual points, but this confidence interval for the mean, it says we got the hot dog question wrong. No, Rachel, are you in another section? Did it show you what you got wrong? Which one did it say you got wrong for the hot dog question? It's so easy to make a little mistake. I obviously make them too. The hot dog one, I'm so sorry. So, oh, no. So when you see that, great thing right there. You don't need the plus or minus one. That's the margin of error it will accept. So you should see, it'll show your answer, and then it'll show, so here, I'll work that one with you, Rachel, real quick. It'll show your answer, and then it'll show like the answer with a margin of error for what it could be. So the number you see, like I had my numbers, oh no, so it won't want the plus or minus. Can you take a screenshot, Rachel, using Command-Shift-4 on your Mac and send it to me, and then I'll take a screenshot of the whole problem with the what it was, use Command-Shift-4, send it to me at bstevens@utk.edu, and I'll make you mod in the chat too. But we'll take a look at that, and I'll see what went wrong, and I'll solve the problem here by hand. So we'll see, oh, okay, my answer was, oh my gosh, it wanted that exact. I mean, it might have been that not enough decimals were carried, but it looks like you did it properly. Maybe, I think you're in another section because ours was due last night. So maybe email your instructor and say, I was super close. I followed all the steps. I think it was a decimal issue. I don't know if your instructors, I give points back when people are super close. It's just, I know how frustrating it can be. Be like, yeah, she probably will. Like, you just ask, you could be like, I'm just wondering. It's just policy by instructor, because I do respond to a lot of emails regarding that. You have to carry a lot of decimals. So especially for that one, carry all the decimals till the end. I always, when you notice, if I solve it, that's why I like doing them in R, because it carries all the decimals for you. If you notice right here, I don't round to my final answer. So it's up to each instructor's policy on how they wish to say, like, make sure you do this, make sure you do that. Phlegm in my throat, don't worry. That's actually not a dry cough, literally phlegm. So that's so bad. Whenever you cough now, you're like, I'm fine. Don't worry, no fever, no nothing. And I've been inside like 24 hours a day, just not shaving. So, okay. Did you finish the chapter 2 quiz? Oh, don't worry. Yeah. Don't worry. Sorry about that. Hey, Caleb, let me make you a mod too. I think assignments got you right there. That's why I make a lot of people mods. So Caleb, sorry about that. Oh, Streamlabs, you need to calm down. I'm gonna make you a mod here, Caleb. we've got stuff in here that will stop people from, like, if someone were to come in here, you're welcome, Rachel. If people were to come in here, oh, not at points like this. You can check your points and stuff like that by just chilling in the chat and asking questions. I love showing that off. It's really fun. But if people were to come in here and say really horrible things, Streamlabs will stop them. So it has a false positive rate. It usually we get false positives from Streamlabs. So don't worry. Sorry, Caleb. Caleb said, did you finish chapter 2, chapters 14, homework and quizzes? So let's do Caleb's question here. Caleb wanted the waiter waitress question. Let's take a look at this right here. So let's hop in here. Caleb, it's good to have you here. So let's go over here. Let's do the waiter waitress question. If anyone has more questions, feel free to ask. This is going to be sampling distributions for sample mean. And that is correct. And it's on, let's go here. Okay. So once again, it really comes down to notation. All of these problems are all about notation. Oh, we got it. First try. Okay. So let's bring back up the chat. And yes, let's do it. You there, Caleb? You ready to do some notation? We got this. So we're going to make the text nice and big so we can see what's going on. And then we're going to get all of our notation. And we go right here. And we're going to bring up our Word document. Ah, wrong. No. Did we just change the question? 1080. Good. We didn't change the question. Okay. And now we have all of our notation. Okay, cool. And you're a mod now, Caleb, so it won't time you out anymore. Sorry about that. It's just like I said, we have measures in place in case someone finds our public stream and were to just come in here and start acting all crazy. Well, too bad. We got things that'll stop them from doing that, so they can't come in here and say nonsense. Or we can also have mods. I can time them out and all that good stuff. So we've got abilities. It's really cool that someone's asking me, like, why are people's names blue with a wrench? Like, they're my moderators. So we can stop nonsense. That's how we moderate our online chats. And so we go right here, we go here, we go here. There's our things we need to identify with notation. I'm just going to move this a little bit out of the way right here. So we have everything going on, ready to go. It's so weird the speedrun timer does that when I bring it off the screen for a second. Speedrun timer, you doing okay? Speedrun timer's doing okay. And so let's take a look at this right here. Okay, so identifying the notation in this problem is key. We have right here that the mean of their tips is this, and the standard deviation of their tips are this. Now, this is asking theoretically what would happen out of a sample size of 40. It's not saying they weighted on 40 tables and found a mean of this and a standard deviation of this. If they weighted on 40 tables and found a mean, they would have y bar and found a standard deviation to be s. But this is not saying they weight on 40 tables. It's saying theoretically they weight on 40 tables. Now, Caleb, crazy question here. If you weighted on 40 tables, what would you expect your average tip on those 40 tables to be according to this problem? What would you expect your average tip on those 40 tables to be according to this problem? For those 40 tables, what would you expect your average tip to be? Any ideas? For those 40 tables, and I'm going to listen to the volume at the end of this, make sure it had good volume. Oh, well, that's the standard deviation. So that would be the variation, but good answer right there. So the standard, you got it. So the mean we would expect, so this is what we would expect for a mean is equal to mu. And then it looks like standard deviation for y bar, which is the variation we would expect, is sigma over square root of n. So now we just have to go in here and mark our notation. So we're just going to erase these right here. Always practice your notation and then know what it means. Well, darn. Yeah, sure, we'll do that. One of these days I'm going to figure out how to make that keyboard never come off again. So we go here and we go 10.80, and then the cool 4.90 over square root of 40. And so that'll get us the standard deviation, which is going to be right next to me. So let's go here and go 40 square root 4.90 divided by, and then 0.7748. 0.7748. And it's right behind my head. Whoa. 0.7748. So there we go right there, 0.7748. And all of this stuff right here. So what do we do with all this? Well, we go to the normal curve and we draw it out. So if we were doing this on a test, we would usually have to draw this out. Unfortunately, we can't do tests like this as of late. We can do a better normal curve than that. So what we would do, there we go, that's a good normal curve, is we would have this curve right here and we'd put the mean and each of the standard deviations. And so just showing you that this can be done by hand. So we'd go here and go 10.80, and then up here would be like 11.57, and we would just keep going up standard deviations. So I kind of just did that quick one in my head right there. But what we're going to do is we're going to go over to David M. Lane. So David M. Lane, where you at? And with David M. Lane, we're going to put the numbers in here. So I'm just literally making my curve this exact same curve by going in here and doing a mean of 10.80 and a standard deviation of what we found. That's not the right standard deviation. This is right here. So if you notice, there's that 11.57. So I'm able to put my numbers in here and see exactly what we're doing. So this is key to this problem, is getting this curve and also going over here and doing it for the other version of it. Now, the two different versions are this one that I'm currently on. Let's go to first. In this one, you put in a number like getting more than $11 on average, getting more than $12 on average, and it tells you the probability of it. Or you could do less than $12. This one right here, you put in a percentage, and it tells you where that's at on the curve. Like that is at 12.602. So we see right here that we can either get a number out of this with this one, which will tell us the average tip we would expect for the top 1%, or this one would say the probability of making above $12. Now, here's where people usually get stuck on this question, is on this question it asks, what's the probability of making $500 on 40 tables? So how much would we need to make on average on 40 tables to make $500? To make $500 on 40 tables, we'd have to make this on average. So Caleb, how much would we have to make on 40 tables to make, to make $500 on average? How much would we have to make on 40 tables? So we have 500 tables, and then $500 we need to make on 40 tables. So $500 we want to make, 40 tables that we want to make them on. How much do we have to make on average? What would be the answer? So think $500 we want to make. We have 40 tables that we have to make it on. I'm going to do a test here at the end. You got it right, Caleb. I'm going to raise the volume up just a little bit right here. It looks like this is doing better. I can't see it out of the corner of my eyes. Cool. I think that's doing a little bit better on the volume. I'm going to see how this is towards the end. I'm going to review the tape. So we need to make 1250. Now we're not going to put 1250 in there. We're going to go to the applet and we're going to go above 1250. Because if we make above an average tip of 1250, then we would make our $500. So we go back to here and we put this in, and then we go right there, and we're good to go on that. So we've got this right here, 4 decimals good. The best 1% of such weekends, here's where people make a mistake, is if we go back to the David M. Lane, people might say, well, the best 1% of weekends, you would make this. But this is going to be our what tip. This is not this is not one tip we make. This is on the best 1% of weekends. This is our what tip, Caleb. This is our blank tip. Think of this is the curve for the blank of the distribution. It's our blank tip that weekend on 40 tables. That is our blank tip on 40 tables. Not like that's not one tip. That's our over a long period of time. The starts with an A or an M. This is our, because this distribution's, you got it, the mean tip. You got it right there. That is the mean tip. So this would be the mean tip we'd have on 40 tables. So we're going to take 40 and multiply it by that, and that's what we'd make on the best 1% of such weekends. We'd make $504.08 because we had an average tip of this on 40 tables. So the best 1% of such weekends, this was our average tip, and we go back to here, we drop it in, we click done, and we make that hundreds. You know we can get those hundreds. You got it. Sorry, going back and forth between my numbers and your numbers is, yeah, so sorry, Caleb, slow down. Look at your numbers. Make sure you get your numbers correct. Great job, Caleb. Does it make some more sense right here? That's what we're going for, is hopefully it makes more sense. Hopefully you understand why and when this applies, all that good stuff. I think that's got it. We did a lot of problems today. 3-hour stream, lots of problems, did some 474. So I might head off here. Yes, awesome. So good. I'm going to head off with one of our, do you have any other questions, Caleb? You're welcome, Marissa. So glad to hear that. Just glad everyone's working hard. Keep asking those questions. Did a lot of questions in the video. And if you want, remember, you get 1,000,000 points for every timestamp you put in our videos. If underneath the video you put a timestamp of when it is. Also, we're lining up an interview for our first stream on Twitch. I might do a test stream or two. You don't want to do a first stream on Twitch and it just fails. So I might do a test stream on Twitch. But that's got it. I think we're good for the day. I'm going to play an outro video here. Just we go fun outro videos. And so I'll see everybody later. I guess tomorrow for class and everything. See you then, and Stat Lab after class.
Here's one thing I like. You can just go up here to the top, and you can go to design and quick layout. And that's my quick layout. It's my favorite one. You can also get some chart title, all this stuff. I think also, I'll show this again real quick. Look at all these options. That's so many cool things. It's so nice.
Gary! I was just looking for the sports channel, Gary.